Welcome to the course. We are here to help you master the architectural complexities of the Oracle FLEXCUBE Universal Banking 12 platform to ensure you succeed in your certification goal. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Oracle Corporation in any way. All trademarks belong to their respective owners. Furthermore, this content is for informational and educational purposes only and does not constitute financial or technical advice. Always consult with qualified professionals before implementing configurations in a production banking environment. In this course, we will dissect every nuance of the FLEXCUBE ecosystem, from its robust multi-tier architecture to the intricacies of core banking parameterization. You will learn to navigate the database schema, manage complex integration touchpoints, and master the extensibility tools that define enterprise banking solutions. By the end of this journey, you will possess the technical depth required to manage, deploy, and troubleshoot this software with complete professional confidence. Achieving this certification is not just about passing a test, as it requires genuine expertise that this course is meticulously designed to provide. If you are aiming to elevate your career and secure your position as a trusted FLEXCUBE administrator, you have arrived at the right place. We value your time, so we strip away the unnecessary noise to focus strictly on what you need to know for the 1z0-413 exam. I look forward to starting this journey with you. Hello, and welcome back to our deep dive into the Oracle FLEXCUBE 12 architecture. In this lesson, we will explore the Extensibility Framework, a foundational component for tailoring core banking operations to specific business requirements. The Extensibility Framework in Oracle FLEXCUBE is built upon the principle of separation between core source code and custom business logic. When we speak of extensibility, we are not suggesting that you modify the core engine directly, as that would introduce significant technical debt and create enormous friction during future upgrades. Instead, the framework provides a structured pathway to inject custom behavior via hooks, triggers, and secondary data structures. Think of it as a strategy pattern applied at the enterprise level, where the system is designed to delegate specific decisions or data operations to user-defined modules. By maintaining this clean boundary, you ensure that the core banking engine remains stable while your specific jurisdictional or institutional requirements are met with precision. Because FLEXCUBE is a sophisticated system, it often relies on metadata-driven design, allowing the framework to incorporate these custom elements without violating the integrity of the underlying database schema. Mastering this involves understanding how the development environment registers these extensions and how the runtime environment orchestrates them alongside standard transactions. To implement an extension, you must interface primarily with the browser-based development workbench, which acts as the abstraction layer for screen generation and data mapping. This workbench allows developers to define new data blocks, capture custom business fields, and perform validation logic without writing raw code for every single UI element. Once a field is added to the metadata, the framework handles the persistence of that data into custom tables or extended columns behind the scenes. It is essential to recognize that this process is heavily reliant on the specific deployment topology you have chosen, as the extensibility engine needs to communicate effectively through the various tiers. If you are handling complex financial data, the framework also enables the implementation of custom logic for cross-validation within the screen design, ensuring that values entered by the teller or back-office staff comply with business rules before hitting the database. This layer of abstraction is what prevents your installation from becoming a brittle mess of hard-coded solutions that break whenever a new service pack is applied. Data source mapping sits at the heart of this framework, acting as the bridge between your custom user interface elements and the back-end database objects. When you create a screen extension, you are essentially defining a contract between a visual representation and an underlying persistent structure, typically stored in PL SQL packages. The Extensibility Framework uses these metadata definitions to automatically generate the necessary SQL queries and PL SQL hooks that facilitate data retrieval and updates. If you neglect the importance of this mapping, you might find that your extended fields are visible on the screen, but fail to persist or validate, leading to inconsistencies in audit trails or reporting. Furthermore, custom menu integration requires you to register your new components within the security framework so that specific roles are allowed to access these extended functions. You must ensure that the access grants reach the database level, meaning your security policies must explicitly account for the custom database objects you have introduced. Understanding this flow from the UI layer through the application server and down to the database schema is what defines professional competence in maintaining a FLEXCUBE environment. When extending these systems, you must also keep in mind the downstream effects on your API and messaging subsystems. If your extension involves capturing new data that needs to be communicated via Swift or via a RESTful service, you will need to map your extended fields into the corresponding XML or JSON payloads. The Extensibility Framework is designed to propagate this information, but you must be diligent about configuring the payload mapping correctly within the gateway components to avoid communication errors. During the batch processing cycles, such as the end-of-day close, any custom logic you have introduced will be executed as part of the total system load. Therefore, inefficiently coded extensions can lead to performance degradation or even systemic batch aborts that ripple across the entire operation. By focusing on the modular nature of the framework, you can keep your custom logic isolated and testable, which is fundamental to system robustness and minimizing long-term maintenance costs. See you in the next lecture. Welcome back to our technical deep dive. In this lesson, we navigate the complex landscape of deployment topologies within the FLEXCUBE architecture to ensure you are fully prepared for your certification. Deployment topologies represent the strategic arrangement of software components across hardware and network infrastructure to meet the demands of a high-availability banking environment. When we talk about FLEXCUBE, we are essentially looking at how to distribute the application server, the database server, and the various client interfaces to optimize both performance and security. A common configuration involves isolating the presentation layer from the business logic layer, which sits behind protected firewalls. By separating these tiers, you reduce the attack surface and allow for independent scaling of your application servers. Each node functions as a part of a larger, cohesive unit that requires precise configuration of listeners and load balancers to ensure seamless traffic distribution. Understanding these boundaries is not just a theoretical exercise, as the exam tests your ability to map components to physical server roles. Whether you are dealing with a single node or a cluster, the core requirement remains the stability of the transactional flow across these designated segments. When architecting these deployments, we must consider the hardware footprint and the logical separation of services, particularly when integrating ancillary modules like trade finance or corporate lending. You should think of the topology as the skeletal structure upon which the entire banking operation rests. The application server layer often runs on web logic, necessitating a robust management strategy for managed servers and clusters. If these servers are not correctly mapped to the underlying data source connection pools, you will inevitably face bottlenecks during peak processing times, such as end-of-day operations. Furthermore, the communication between the web server and the application server layer relies heavily on specific protocols that must be hardened. You should visualize the data path from the user's browser, through the load balancer, into the application server, and finally to the database schema. Every hop in this chain is a potential point of failure that requires monitoring and redundant paths to maintain the high availability demanded by financial institutions. Beyond simple connectivity, the deployment topology directly influences how you handle patch management and version upgrades. If your architecture is rigid, updating a single component could necessitate a full system outage, which is unacceptable in contemporary banking scenarios. By utilizing a modular deployment approach, you can perform rolling updates where specific instances are taken offline for servicing while the remainder of the cluster continues to handle incoming traffic. This requires a sophisticated configuration of session persistence, ensuring that a user state is not lost if their request is rerouted during a deployment cycle. You must also consider the placement of auxiliary services, such as the API gateway and the messaging subsystems, which often sit in a DMZ-like perimeter to facilitate secure external communications. Improper placement here creates significant security vulnerabilities that could compromise the integrity of your core banking data. Consequently, your mastery of these deployment patterns is essential for maintaining both a performant and a compliant banking system. As you study for the exam, remember that the complexity of your deployment should always be proportional to the throughput requirements of the institution. Avoid over-engineering setups that introduce unnecessary latency, yet never sacrifice the redundancy required for business continuity. Every component integrated into your topology, whether it is an integration layer for Swift messaging or a dedicated reporting instance for OBDX, must have a defined connectivity rule. You should focus on how these logical components map to the physical CPU, memory, and storage constraints of your infrastructure. Practice visualizing these interactions as if you were troubleshooting a live environment where a specific tier has become unresponsive. If you can define the boundaries and the traffic flow, you will easily handle the architectural challenges posed by the certification questions. Mastery of these topologies is the fundamental difference between a configuration that merely works and one that excels in a production-grade banking ecosystem. See you in the next part of our series. Welcome back. Today we examine the multi-tier architecture within the FLEXCUBE Universal Banking environment, a prerequisite for your certification success. In an enterprise banking system like Oracle FLEXCUBE, the concept of a multi-tier architecture is not merely an optional design choice. It is a fundamental requirement to ensure scalability, security, and maintainability. At its core, this architecture separates the system into distinct logical and physical layers, specifically the presentation tier, the application tier, and the database tier. The presentation tier serves as the interface between the user and the system, often rendered through a web-based client that interacts with the application server. This layer is responsible for translating user inputs into application-specific requests while shielding the user from the complexities of back-end transactions. By isolating the presentation logic, architects ensure that updates or changes to the user interface do not compromise the integrity of the underlying business logic. It provides a clean separation that allows designers to focus on usability without worrying about how those screens interface with the core banking database. Moving into the application tier, we encounter the engine of the FLEXCUBE architecture, which hosts the FLEXCUBE Universal Banking application code. This middle tier is where the business rules reside and is typically deployed on a robust application server like Oracle WebLogic. It acts as the intermediary, processing requests from the presentation layer and performing the necessary calculations or validations before interacting with the database. One significant advantage of this middle layer is its ability to handle session management, caching, and stateful processing, which are critical for performance in a high-concurrency banking environment. When a customer initiates a transaction, the application tier validates the request against the core banking parameters and then generates the SQL or PL SQL calls required for the database. By offloading these tasks from the client and the database, the system gains the ability to scale horizontally, allowing us to add more application servers as transaction volume increases. The database tier sits at the bottom of the stack and serves as the persistent repository for all banking data, including customer profiles, accounts, and transaction history. Within the context of FLEXCUBE, this tier leverages the power of the Oracle database to manage high-volume transactional data with strict ACID compliance. The interaction between the application layer and the database is governed by data source mappings and specific PL SQL packages that ensure data integrity remains absolute. Because this layer maintains the schema structure and core data dictionaries, it is configured for high availability and recoverability to ensure that financial data is never lost. We often see complex synonym management and explicit access grants here to maintain a secure boundary between different modules. Ensuring the efficient mapping of these components is vital, as any bottleneck at the database level will propagate upwards and significantly degrade the end-user experience across the entire system. Understanding how these tiers communicate with one another requires a look at the middleware and the communication protocols that bind them. FLEXCUBE utilizes standardized protocols to ensure that data flows seamlessly from the web client through the application server and into the database. This is where configurations regarding REST and SOAP API integrations frequently intersect with the architectural design, as these services often act as entry points into the application tier. If we consider the flow of information during an end-of-day process, the application tier must manage multi-threaded requests while simultaneously ensuring that global database locks are handled correctly to prevent corruption. The architecture is designed to manage this traffic through optimized connection pools and listener configurations that reduce the latency inherent in network-based tiers. By mastering this tiered approach, you not only prepare yourself for the examination, but also gain the required intuition for troubleshooting complex system timeouts and performance degradation in real-world scenarios. I will see you in the next lecture. Welcome back to our exploration of the FLEXCUBE architecture. In this lesson, we will focus specifically on the nuances of application server configuration required for a stable deployment. When we approach the application server configuration for Oracle FLEXCUBE, we are essentially defining the runtime environment that hosts the enterprise Java components. Because FLEXCUBE is built as a G-compliant application, the stability of the entire core banking system is strictly coupled to the application server settings. You must first ensure that the managed server instances are configured with appropriate heap memory allocation to accommodate the high concurrency demands of banking transactions. It is not merely about increasing memory, but rather about tuning the garbage collection strategy to minimize pause times during peak hours. Furthermore, the data source connections managed by the application server act as the bridge between the application logic and the Oracle database. If these connection pools are not sized correctly, your system will inevitably encounter bottlenecks during EOD processing. You need to inspect the connection pool properties, specifically focusing on initial capacity, maximum capacity, and the statement cache size, to ensure that the database is not starved of requests. We also have to consider the environment variables and the Java properties that define the integration points for external subsystems. Misconfiguration here often leads to deployment failures or, worse, latent errors that only appear when a specific module like trade finance attempts to reach out to the messaging gateway. One of the most critical aspects of application server configuration involves the deployment of the EAR file through the console or via automated scripting tools. You must pay close attention to the class loading order, as conflicts between the server-provided libraries and the FLEXCUBE-specific jars can cause unpredictable behavior. In a multi-tier architecture, the application server might be physically separated from the web server, which requires us to tighten the security headers and timeout parameters. For example, if your session timeout on the application server is lower than the timeout configured on the load balancer, users will experience frequent, unexplained session drops. Another vital component is the optimization of the HTTP listener or the proxy settings that handle incoming requests from the UI layer. When you modify these settings, you are directly impacting how the system processes concurrent user sessions during busy banking hours. Always remember that the application server provides the container, but it is your configuration that dictates whether that container is a bottleneck or a facilitator of high performance. By systematically reviewing the server logs and the resource monitors, you can identify if there are threads waiting on external resources, which often points towards a misconfigured data source or a slow network integration. Transaction management is another pillar of application server configuration that you must master for this exam. Since FLEXCUBE handles atomic financial transactions, any misalignment in the JTA configuration can potentially lead to data inconsistency if a distributed transaction fails across different modules. You need to verify that the transactions are correctly scoped and that the timeout limits are reasonable enough for complex operations like loan disbursements or multi-currency transfers. Furthermore, the integration with messaging subsystems relies on the application server's JMS resources. During your configuration check, you should assess the persistence settings of these queues, as they determine whether your system can reliably recover after an unexpected server restart. I strongly advise you to map out your server dependencies early, as external integrations often require specific environment entries in the deployment descriptor. By understanding the interaction between the application server's internal registry and the FLEXCUBE infrastructure, you will be better equipped to troubleshoot deployment stability issues. This level of technical oversight is what separates a standard installation from a professional-grade, high-availability core banking setup that satisfies all regulatory and operational requirements. I will catch you in the next session. Welcome back. In this session, we will examine the mechanisms required to maintain high availability within a FLEXCUBE Universal Banking environment. High availability is not merely a feature you toggle in a configuration file, but rather an architectural mandate born from the necessity of uninterrupted financial service. In the context of FLEXCUBE, our goal is to eliminate single points of failure by ensuring that every layer, from the client-facing application server down to the persistence layer, possesses redundant capabilities. When we talk about high availability, we are discussing the deployment of clustered application servers that operate in concert to handle concurrent user requests. This involves configuring the managed servers within a domain to load balance traffic effectively through a hardware or software load balancer. Without this load distribution, a single server node failure would result in immediate service degradation, which is unacceptable in core banking operations. By distributing the load across multiple nodes, we ensure that session state is preserved or replicated, allowing the system to fail over seamlessly without forcing a user to re-authenticate or lose their current transaction progress. Effective high availability also relies heavily on the underlying Oracle WebLogic infrastructure that hosts the FLEXCUBE application. We must consider the synchronization of caches and the persistence of HTTP sessions across the cluster nodes, which is achieved through the configuration of cluster-wide messaging and session replication. If your infrastructure lacks a robust heartbeat mechanism between nodes, the cluster may suffer from split-brain scenarios where multiple servers attempt to lead the same task, resulting in data corruption or transaction inconsistency. We manage this through careful definition of the cluster internal communication channels and ensuring that timeout thresholds are tuned to the latency characteristics of your network. Reliability here is a product of these meticulous settings. Ignoring them invites the exact failures we are trying so hard to design around. You should look at the resource management within WebLogic and verify that the data sources used by FLEXCUBE are configured to leverage Oracle RAC or real application clusters to provide the necessary database layer redundancy. Database tier is arguably the most critical component when considering the overall system availability of a banking platform. Oracle RAC enables multiple instances to mount the same database files, providing a level of resilience that standard single-instance setups simply cannot replicate. In a high-availability FLEXCUBE setup, the application server interacts with the database via grid-link data sources, which are specifically designed to be aware of the Oracle RAC configuration to provide fast connection failover and runtime connection load balancing. This means that if a database instance fails, the application is signaled immediately to move its traffic to surviving nodes, minimizing the window of downtime. It is essential to understand that this requires specific listener configurations on the database side and accurate ONS, or Oracle Notification Service, settings on the application side. When these pieces are aligned, the banking system can survive the loss of an entire database node without disrupting the front-end user experience, which is the gold standard for production reliability. Transitioning from the network and database layers to the application tier requires us to consider the configuration of the EAR files that contain the FLEXCUBE deployment. Each node in the cluster must be configured identically to prevent discrepancies that could lead to intermittent errors when users traverse different parts of the application. Configuration files, including those defining the messaging subsystems and the connection factories, must be kept in absolute parity across all nodes to ensure the deployment remains stable under load. We use centralized configuration management where possible to avoid the configuration drift that often accompanies manual updates to a large cluster. Periodic audits of these deployments are recommended to ensure that no stray configuration changes have been made in a development or testing environment that could inadvertently find their way into a production high-availability cluster. This systematic approach is the only way to ensure that the system remains both performant and resilient throughout its lifecycle. Beyond the hardware and infrastructure software, we must address the transaction management across these distributed systems. Since high availability implies multiple points of execution, the integrity of distributed transactions, those involving multiple modules like CASA and trade finance, becomes a significant concern. We rely on the Java Transaction API to manage the commit and rollback phases across heterogeneous resources, ensuring that the system remains in a consistent state even if a service node fails mid-transaction. Understanding the XA protocol support within your messaging and database drivers is paramount here, as it dictates whether the platform can reliably support distributed transactions. If your architecture is tuned performantly but fails to handle these transaction boundaries correctly under a node failure, the high availability setup will have merely succeeded in creating a faster way to corrupt your banking data. Consistency is always the priority, which means our high availability design must be subservient to the strict atomicity requirements of financial ledger entries. See you in the next lecture. Welcome back. In this session, we will focus on troubleshooting the core architectural components of the FLEXCUBE Universal Banking 12 environment. When we approach the architecture of a complex system like FLEXCUBE, troubleshooting is often less about finding a single bug and more about understanding the flow of data through layered abstractions. You must begin by viewing the application server configuration as an extension of the JVM environment rather than just a container. If you encounter unexpected behavior, the first point of failure is frequently the decoupling layers where the WebLogic managed servers interact with the database connection pools. It is crucial to verify that the data source mappings are not only configured correctly in the server console, but are also reflecting the intended connection string properties. Sometimes, the physical connection to the database remains open, but the logic within the application tier fails to retrieve a valid session due to stale credentials or expired grants. You should systematically check the deployment status of the various EAR files to ensure all libraries are correctly path-mapped and accessible by the underlying application runtime. By isolating the application server layer, you eliminate the possibility that the issue resides within the database schema or the PL SQL packages themselves. Database-side troubleshooting requires a deep understanding of how FLEXCUBE interacts with the underlying Oracle schema through synonyms and grants. An architectural failure often manifests as a ORA00942 error, which immediately points toward a breakdown in the expected privilege structure. You need to verify that the runtime user has the correct synonyms for the core packages, because these packages are the engines that drive every transactional operation. When the database dictionary indicates that a package is valid, but the application reports an execution error, look toward the cross-schema dependencies. If a recent patch application failed, or a migration protocol was improperly executed, the link between the application code and the database dictionary might be severed. Always examine the state of invalid objects, particularly those associated with the core banking modules, as these are frequently the culprits when global functions stop responding. Troubleshooting these architectural artifacts requires you to be comfortable navigating through the database views to ensure that the grants are indeed current and mapped to the right roles. Messaging and API integration points represent another significant surface area for architectural friction, especially when dealing with REST or SOAP gateways. When an XML payload fails to map correctly to the internal request structure, the bottleneck is often found at the API gateway layer or within the translation logic. You should start your diagnostic process by inspecting the gateway logs to see if the payload is being rejected before it even reaches the application tier. If the payload arrives but processing halts, the issue moves to the transformation service where XML schemas are validated against the internal definitions. Misconfiguration of the messaging subsystem, such as a mismatch between the expected SwiftMT or MX standards and the configured interface, will often lead to stalled transactions. Relying on stack traces from the integration server is a valuable diagnostic step, but treat them as symptoms rather than the root cause. You must reconcile the payload structure against the API metadata to ensure that fields defined in the gateway match the required inputs for the specific transactional service. Finally, batch processing and session management provide a distinct set of challenges that are best diagnosed through the lens of multi-threading and system resource contention. When an end-of-day process aborts prematurely, the diagnostic focus should immediately shift to the thread state and any locking contention occurring at the database level. Often, the failure originates from an accumulation of orphans in the session management tables, which prevents the batch from securing the necessary locks. By analyzing the batch diagnostic logs for specific error codes, you can determine if the abort was caused by a memory threshold violation or a deadlock scenario. Performance tuning in this context means observing how the transaction load is distributed across the available threads and adjusting the parallelism settings to prevent resource exhaustion. Even in high availability setups, an improperly tuned batch job can trigger a cascade failure that impacts the entire infrastructure. Debugging these systems necessitates a methodical review of the deployment topologies to ensure that the batch threads are appropriately balanced and isolated from the user-facing request processes. Until we meet again. Welcome back to our journey through the technical architecture of Oracle FLEXCUBE. Today, we are shifting our focus to the fundamental configuration layer known as banking parameterization. To understand banking parameterization, we must first recognize that FLEXCUBE is not a monolithic application that works out of the box without contextual guidance. Instead, it functions as a highly configurable engine that requires specific operational definitions to behave according to banking regulations and internal institutional policies. Think of this as the difference between a raw calculation engine and an accounting system that understands the nuances of tax years, currency denomination preferences, and fiscal calendars. When we talk about parameterization, we are discussing the maintenance of data that dictates how the core banking modules process transactions. This data is not transactional in nature. Rather, it is the metadata that governs the life cycle of every deposit, withdrawal, and loan calculation performed within the system. At the architectural level, these parameters are stored in specialized core tables that the application accesses during runtime to validate business logic. For instance, consider the setup of a branch within the system, which requires defined identifiers, local currency mappings, and time zone configurations. If these parameters are not accurately defined, the system cannot correctly calculate the movement of funds or perform the end-of-day balancing processes. We are looking at a system where the architecture relies heavily on cross-reference tables that connect GL structures to specific banking products. It is essentially about defining the boundaries of what is possible for a specific environment, ensuring that the software remains compliant with the legal and operational framework of the bank using it. The complexity increases when we account for the modular nature of FLEXCUBE, as parameters often need to be consistent across various functional areas. When setting up a new banking product, you must link it to the appropriate accounting entries, which necessitates a clear understanding of the chart of accounts. We manage this through a series of maintenance screens that ultimately push data into back-end tables through controlled PL SQL layers. These data points dictate the behavior of interest accrual cycles, which must be aligned with both the core database records and the external reporting requirements. If you change a parameter mid-cycle, you must understand the ripple effect that this change has on existing account balances and ongoing transactions. We also need to consider the validation logic that ensures these parameters are not entered in a way that would trigger system instability or accounting errors. Most of these inputs undergo strict validation checks at the application level before they ever touch the database, preventing invalid configurations from being saved. This involves verifying that the relationship between, for example, a currency code and an exchange rate provider is valid within the context of the current branch setup. From a troubleshooting perspective, if a module fails to execute a specific transaction, the first place we look is the parameter maintenance. Often, a missing mapping or a misaligned date parameter in the global configuration will manifest as an unexpected error in the integration layer later on. Data integrity during parameterization is managed by distinguishing between static and dynamic data structures. While parameters define the rules, they must also allow for the flexibility that modern banking demands, such as handling fluctuating market rates or sudden policy changes. Within the FLEXCUBE ecosystem, this is handled by maintaining distinct levels of authority, where core system parameters are often restricted to administrative roles. This hierarchical approach to configuration ensures that only authorized personnel can alter the rules that govern the ledger. As we proceed through our technical examination, keep in mind that the database schema is built to support this parameterization through highly indexed tables designed for fast read access. Efficiency in this area comes from understanding the schema structure and knowing exactly which tables hold the functional parameters. When you are tasked with verifying a configuration, you are essentially performing a manual audit of these records to ensure they align with the business requirements defined in the functional specification. The goal is to ensure that the system handles the vast complexity of global banking with a consistent, deterministic approach to every calculation. We must view every parameter as a constraint that helps the system maintain its integrity across multiple modules, from CASA to complex trade finance workflows. By mastering this layer, you gain the ability to troubleshoot complex issues that originate from underlying setup inconsistencies rather than programmatic bugs. See you in the next lecture. Welcome back. In this session, we will examine the technical intricacies of CASA integration within the FLEXCUBE architecture to ensure your system behaves predictably. Integrating current account and savings account modules into the broader banking landscape requires a disciplined approach to parameterization and data flow. When we look at CASA, we are not just managing simple account balances, but orchestrating complex interactions between core banking modules and external interfaces. The underlying architecture relies heavily on consistent schema structures and the proper mapping of data sources across the multi-tier deployment. If your data dictionary navigation is not precise, the integration of new account products will inevitably fail during transaction processing. You must ensure that the PL/SQL packages governing interest accruals and transaction postings are aligned with the global bank parameters defined at the system level. This is where architectural rigor beats guesswork, as any misalignment here surfaces as persistent reconciliation errors in the general ledger. The actual integration process hinges on how we handle the messaging subsystem and API gateways. Whether you are dealing with SOAP or RESTful endpoints, the XML Payload Mapping must strictly adhere to the FLEXCUBE data contract to prevent runtime parsing exceptions. It is rarely the fault of the message itself, but rather the lack of proper synonym management and database grants that prevents the application server from committing the transaction to the database. Think of the integration layer as the nervous system of the bank. If the latency within your API gateway exceeds threshold limits, the end-user experience on the UI layer will degrade rapidly. We often see practitioners struggle with custom menus and field validations because they fail to map the data source correctly to the backend entity definitions. By maintaining a clean separation between the presentation layer and the persistent database schema, you reduce the surface area for potential integration bugs. Performance tuning for CASA-heavy environments requires an intimate understanding of multi-threading and end-of-day batch processing. During high-volume periods, the load on the database increases significantly, and if your session management tools are not optimized, you will experience contention on critical tables. This is especially true when batch processing triggers complex calculations across multiple modules, such as when CASA records interact with trade finance or loan modules. Troubleshooting these integrated processes involves auditing the transaction logs for any aborted threads and correlating them with the audit trail configuration. Always verify that your password policies and role-based access controls remain intact across the integrated modules, as security gaps often appear at the points where disparate systems stitch together. Robustness is not accidental. It is the result of meticulous configuration and consistent testing of the data flow between the CASA module and the rest of FLEXCUBE ecosystem. See you in the next lecture. Welcome back. Today, we are diving into the Loans module and its critical role within the broader FLEXCUBE architectural ecosystem. When we talk about the Loans module, we aren't simply documenting how to create a loan contract. We are examining the systemic integration requirements that define lifecycle banking operations. The module relies heavily on the core banking parameters established during initial environment setup. If these parameters are misaligned with your product definitions, the downstream impact on accrual processing and interest calculation becomes catastrophic. You must understand how the loan account serves as the central node for interest schedules, payment hierarchies, and penalty management within the core schema. We achieve this by mapping the product categories to specific general ledger structures, which then propagate transactional data across the entire database instance. Consistency here is paramount, as the interdependency between the loan account and the existing CASA accounts for drawdown and repayment creates complex, multi-directional data flows. These flows are not just administrative. They are functional requirements that the underlying Oracle PL SQL service layer must validate in real time. Effective lifecycle management of a loan requires a deep appreciation for how the system handles status transitions and event-driven accounting. Each event, whether it is a disbursement or a periodic schedule payment, triggers a cascade of accounting entries that must balance within the general ledger. We manage these triggers through the event-to-accounting entry mapping, which ties our business logic to the core financial accounting subsystem. When you configure these products, you are essentially defining the rule engine for the system's runtime environment. It is helpful to visualize this as an object-oriented composition where the loan product acts as an interface implementation for various lending scenarios. The system architecture expects that your defined event codes possess clean, unique identifiers within the data dictionary to ensure that cross-module lookups remain performant. If you fail to maintain this granular level of configuration, you will inevitably encounter inconsistencies during the batch processing cycle. Moving beyond simple definitions, we must consider how the Loans module interacts with the broader messaging and API gateways. In a modern deployment, a loan disbursement request often originates from an external system via a REST or SOAP interface. This requires your XML payload mappings to be precisely calibrated to the internal schema expected by the loan process workflows. We use the gateway integration layer to sanitize and transform these external inputs into internal transactional triggers. By decoupling the transaction initiation from the core banking host, We gain significant operational flexibility, but this also shifts the burden of validation onto the gateway. You have to ensure that the SOAP or REST request contains sufficient metadata to satisfy the security and role-based access requirements enforced by the system. Failure to pass these authentication tokens at the gateway level will result in rejected transactions long before they reach the loan module's logic layer. Finally, let's discuss the critical nature of error handling and audit trailing within this specific module. Every action performed on a loan, from interest rate refixing to penalty waiver, must be logged effectively to satisfy administrative and compliance audits. The audit trail is not merely a record of actions, it is a fundamental part of the system's state management, allowing for reconciliation and backtracking of financial impacts. When we look at performance tuning, especially during the end-of-day batch processing, the index usage on loan tables becomes the most critical performance factor. We often find that poorly optimized queries during interest accrual are the result of fragmented data storage or missing synonyms within the database structure. Proper management of these database entities alongside regular maintenance of the system's session management tools ensures that your lending operations remain robust even under high transaction volume. We build these systems to be resilient, and that resilience starts with the correct configuration of these foundational settings. I look forward to our next session. Welcome back to our exploration of the FLEXCUBE architecture. Today we dive into the trade finance module integration and its underlying systemic dependencies. The trade finance module within FLEXCUBE serves as a complex extension of the core banking engine, requiring a nuanced understanding of how global trade instruments, such as letters of credit, bank guarantees, and documentary collections, interface with the ledger. Unlike internal ledger movements, trade finance operations are inherently tied to messaging subsystems like SWIFT for MT or MX format delivery, necessitating a robust integration layer between the module and the external communication gateways. When you are configuring this module for the exam, remember that the linkage between branch parameters and the trade finance specific parameters is the primary driver of operational behavior. Each trade product must be mapped to the appropriate GL, general ledger, accounts defined in the chart of accounts, as this ensures that contingent liabilities are tracked accurately off balance sheet until they are settled or expire. You must understand that trade finance is not a siloed module. It relies heavily on the core static data, such as customer information files, CIF, and account class definitions, to execute transactions effectively. If the customer profile is not correctly set up with the necessary limits and risk classifications, the module will fail to permit the issuance of trade financial instruments. This necessitates a deep dive into the limit maintenance screens, where you define the collateral and risk participation thresholds that govern your bank's exposure. Data source mapping becomes particularly critical when we consider the interaction between the trade finance module and the rest of the FLEXCUBE environment. You will find that many administrative tasks involve updating the database with specific PL SQL packages that handle the life cycle of a bill or a guarantee, from initialization through to maturity. It is not enough to simply configure the UI. You must be cognizant of the underlying data dictionary and how schema objects are structured to support multi-currency handling. In a production environment, the trade finance module must be treated as a high-throughput engine, meaning that performance tuning for these specific transaction flows often involves optimizing the execution plans for queries involving large trade contract tables. You should be prepared to discuss how the system handles the reconciliation of trade messages against the core accounting entries. This involves verifying that the SWIFT gateway has received a valid response code before the system finalizes the status update on a specific trade instrument, which is a common stress point for system stability. Furthermore, if you encounter difficulties during the EOD processing of trade contracts, it is almost always linked to a mismatch in the settlement dates or a lack of liquidity in the Nostro accounts mapped to the trade product. The Extensibility Framework allows us to add custom fields or validation logic to trade finance screens without modifying the base source code, a concept that is frequently tested. When you extend a view, you are essentially leveraging the FLEXCUBE development workbench to bind new screen elements to data sources that persist into the underlying database schema. This capability is vital for banks that require specific compliance data fields for local regulations that are not part of the standard global product. You should know how to properly map these custom user interface elements to the database level via the data source maintenance, ensuring that the necessary synonyms and grants are present for the application server schema to access these new tables. Failure to correctly manage the database grants often leads to runtime errors that only manifest when a user attempts to save a transaction after the data capture phase. It is also important to maintain consistency in your validation rules, as complex trade workflows often involve multi-step approval processes that move through different states defined in the repository. Keeping the system architecture clean while adding these layers of complexity is the true test of your competency with the platform. See you in the next lecture. Welcome to this lesson on cross-module data. In this section, we examine the complexities of how FLEXCUBE shares information across distinct banking modules to maintain a consistent state. When we approach the challenge of data integration within a banking architecture, we must first recognize that FLEXCUBE operates as a highly modular ecosystem where autonomous components often need to reconcile their states with common repositories. This is not merely about moving data from one table to another, but rather about maintaining the integrity of financial records that span across distinct functional boundaries such as CASA, loans, and trade finance. At the heart of this cross-module flow lies the necessity for a shared definition of entities like customers, limit structures, and accounting entries. If a customer updates their address or risk profile in the CASA module, that change must propagate effectively to the loans module to ensure that the credit appraisal process reflects current status. This synchronization is usually orchestrated through a combination of shared database schemas and middleware event handling that captures state changes in real time. By utilizing these mechanisms, we avoid the pitfalls of redundant data entry, which is the primary driver of operational risk in large-scale banking environments. It is important to view these modules not as isolated silos, but as interconnected services that rely on a central data dictionary to interpret shared attributes correctly. When you are configuring these interactions, you are essentially setting up a distributed ledger system within the application architecture, where every write operation must respect the dependencies that exist across module borders. The actual orchestration of this data often relies on specific metadata objects that define how tables should interact during transaction processing. In FLEXCUBE, the concept of a shared context is managed through internal mapping files that define the visibility of specific data sources across different functional zones. When a transaction triggers an update, the system must navigate through these mapping configurations to ensure that the secondary modules receive the necessary notifications or data pushes. This involves an understanding of the underlying table structures where cross-module links are often handled through common keys or synthetic bridging entities. Developers and administrators must monitor these pathways closely, as performance bottlenecks frequently emerge when there is significant contention for access to these shared data points. Furthermore, when you are designing or troubleshooting these interactions, you must consider the transaction scope, ensuring that if a CASA account is updated, the associated entries in the general ledger remain atomic. This atomicity is the primary goal because a partial update that leaves one module out of sync with another can lead to massive reconciliation efforts during the end-of-day operations. Relying on the built-in hooks provided by the application framework is generally preferred over manual database manipulation, as these hooks are specifically designed to honor the business logic that governs intermodule accounting. Extensibility tools play a pivotal role here, particularly when you need to introduce custom data fields that must traverse multiple functional modules. When you append a field to a customer profile, you are not simply changing the UI. You are modifying the downstream impact of that data on credit limits, tax reporting, and risk aggregation engines. This transition requires the use of the Extensibility Framework to generate the necessary underlying schema changes and ensure that the database objects are automatically adjusted and mapped. A common mistake occurs when implementers focus entirely on the screen layer, forgetting that the database layer must also carry those custom attributes through all relevant modules. You should verify that your data mapping includes the necessary access grants for the various service accounts that run the background processes for each module. Without proper grants on these shared views or temporary tables, you will likely encounter silent failures where the data appears to reach the application but fails to settle in the destination module. Always validate that the metadata configurations are consistent across all environments, as differences in the development, testing, and production environments are a common source of complex integration errors that are notoriously difficult to reproduce during post-deployment phases. See you in the next lecture. Welcome back. We are now moving into the critical domain of integration testing within the FLEXCUBE architecture. This session will ground our understanding of how disparate system components must interact to ensure transaction integrity. When we approach integration testing in a complex ecosystem like FLEXCUBE, we are essentially verifying the communication boundaries between various modules. It is rarely enough to verify that a single PL SQL package executes its business logic in isolation. Instead, we must confirm that the data passed from the CASA module, for example, successfully triggers the appropriate ledger entries in the core accounting engine. This requires a rigorous assessment of how the application server handles inter-process communication. We must observe how the database schema mapping layers respond when we introduce cross-module requests. If our data dictionary settings are improperly configured, the validation layers will fail the transaction before it ever hits the persistent storage, leading to subtle bugs that are difficult to trace in a production environment. Effective integration strategy requires us to look specifically at the messaging subsystems that define the modern banking landscape. Whether we are dealing with a local SOAP web service call or a complex Swift MT or MX message delivery, the test must validate the underlying XML payload mapping. We often see developers focus entirely on the API gateway without considering the synchronous or asynchronous nature of the message queue. If our REST API layer is tuned for performance, but our backend database synonyms are restricted by incorrect access grants, the connection will time out under load. Testing must therefore involve simulating high-throughput scenarios to verify that our multi-threading configurations during end-of-day processes do not lock critical database rows. This is where the marriage of architectural theory and granular database control becomes essential for the system to remain robust. Security integration testing is frequently overlooked until a late stage, but it should be considered a first-class concern from the start. We must verify that our role-based access control policies are strictly enforced across every module intersection. If a user has the appropriate authorization to initiate a trade finance transaction, the underlying integration must confirm that the same user credentials satisfy the audit trailing requirements for compliance purposes. I suggest testing these scenarios by deliberately attempting to cross boundaries that should be restricted. By monitoring the session management tools during these tests, we can determine if the application server is correctly handling the identity propagation across the multi-tier architecture. It is this systematic approach to verification that distinguishes a stable banking deployment from one prone to recursive troubleshooting of obscure security alerts. Finally, we must address the reality of batch processing and its integration with reporting platforms like OBDX. The flow of data from the core accounting modules into the reporting schema is susceptible to failures if the patch deployment versions are out of sync, or if the database schema structures are fragmented. Our integration tests should ensure that the batch status remains consistent during the transition between the beginning of day and end of day cycles. A failure to validate these handoffs usually manifests as report inaccuracies, which are often mistakenly diagnosed as UI screen validation errors. We must maintain a clear operational view of the data path from the initial transaction entry point through to the final persistent record. By focusing on the interaction points rather than individual components, we ensure a holistic level of system integrity. I will see you in the next lecture. Welcome to this module, where we will examine the foundational requirements for configuring the Oracle database to support the FLEXCUBE architecture. Mastering this setup is essential for ensuring system stability and performance across your banking modules. Before we dive into technical execution, we must recognize that the database is not merely a storage layer for FLEXCUBE, but the active engine driving core banking operations. When preparing the environment for a 12c installation, the initial focus must be on the optimal initialization parameters, specifically memory management through automatic memory management, or the more granular automatic shared memory management. You should ensure that the SGA and PGA targets are appropriately sized to accommodate the high concurrency demands of a financial application. A common pitfall during setup is neglecting the proper configuration of character sets, such as AL32 UTF-8, which is mandatory for internationalized banking transactions and consistent data representation. Additionally, the creation of appropriate table spaces is critical. as you must logically separate core FLEXCUBE data, indexes, and lob segments to prevent contention and facilitate performance tuning. Always remember that the database must be configured with a block size that aligns with the specific storage I/O requirements of the high transaction environment. During the installation phase, the deployment of the Oracle FLEXCUBE schema involves executing a series of scripts that establish the repository architecture. This process is deeply integrated with the database objects, necessitating that you verify the existence and correct configuration of various database profiles and shared pool settings before starting the schema imports. The architecture relies heavily on specific objects, such as sequences and triggers, to handle transaction IDs and auditing requirements automatically. When you consider the schema footprint, you must also be mindful of the undue tablespace sizing because long-running EOD processes can quickly exhaust undue logs if they're not provisioned with sufficient headroom. Furthermore, the role of the database instance in this context involves not just the static schema definitions, but the dynamic interaction between the application server and the PL SQL engine. Configuration in the listener or the tnsnames aura file can often masquerade as application layer errors. So validating the network connectivity and service registration early is a crucial diagnostic step. Security and compliance are woven into the fabric of the database setup process from the very start. Even before you load the branch or customer information into the system, you need to enforce strict user authorization protocols that govern who can interact with the underlying schema objects. This involves creating dedicated service accounts for the application server with the minimum set of privileges required to execute stored procedures, rather than granting excessive DBA roles. You should also implement audit policies at the database level to track DDL changes, which provides a critical layer of traceability for compliance reporting. Encryption of data at rest, utilizing transparent data encryption, is another standard recommendation when dealing with sensitive financial datasets. By establishing a robust security posture at the database level, you provide a stable foundation for the higher-level role-based access control mechanisms that exist within the FLEXCUBE UI. Planning for these security parameters during the initial setup preserves the integrity of your modular banking environment as it scales across different regions and business units. I look forward to discussing the schema structure in our next session. Welcome back. We are going to dive deep into the specific layout and organization of the database environment in this section. We will examine how the underlying layers maintain data integrity and support complex banking operations. The schema structure in Oracle FLEXCUBE Universal Banking 12 is intentionally fragmented to maintain a clear distinction between core system parameters, transactional data, and local site-specific customizations. When you operate within this environment, you are essentially interacting with a highly normalized relational model that prioritizes referential integrity above virtually all else. The system utilizes a schema per module approach in many instances, which allows for better management of distinct banking functions, such as current accounts and savings accounts, or specialized areas like trade finance. This modularity means that when we look for entity relationships, we must understand the dependency chain that links table structures across these logical boundaries. You will find that the base schema contains the fundamental definitions, while the integration layer manages the mapping required for cross-module communication. Understanding this structure is not merely an academic exercise. It is a prerequisite for executing any meaningful performance tuning or troubleshooting when the database becomes a bottleneck. Without a firm grasp of how these tables relate to one another, attempts to reconcile data or optimize query execution will almost certainly fail. At the heart of the schema, we find the core banking tables which house the static and dynamic data points vital for daily operations. These tables are often partitioned based on business dates to ensure that historical data does not degrade the performance of current processing cycles. When working with these structures, you are expected to navigate through synonym layers that abstract the actual physical location of the data. This abstraction is beneficial because it enables the application server to interact with the database without being tightly coupled to a specific schema owner, facilitating smoother transitions if you migrate your deployment. Beyond the standard relational tables, the schema incorporates complex PL SQL packages that act as the gatekeepers for data entry and modification. These packages contain the business logic that ensures a transaction conforms to the strict regulatory and functional rules defined within the parameterization modules. If you attempt to update underlying tables directly, Circumventing these established APIs, you risk corrupting the core banking state and violating the architectural integrity that the product is designed to maintain. We must also consider the role of metadata and dictionary tables that facilitate the extensibility framework. FLEXCUBE relies on these internal structures to interpret data source mappings and UI-driven requirements dynamically. When you perform any customization affecting screen fields or internal validations, you are actually modifying these metadata tables, which then inform the transaction processing layer how to handle the new inputs. This metadata-driven approach implies that the schema acts more like a repository for application configuration than just a simple store for ledger entries. The interaction between these configuration tables and the transactional tables is mediated by a sophisticated web of foreign keys and triggers that ensure nothing happens in isolation. Consequently, deep knowledge of the data dictionary is required when you are tasked with extending the functionality of a module. You need to know exactly which metadata entry points determine the behavior of a specific transactional field to avoid unintended side effects that might cascade across the entire banking system. When analyzing the schema from a broader deployment perspective, we realize that the physical distribution of these objects is critical for high availability and load balancing. The database must be configured to support multi-threading at the application tier, which means the locking mechanisms and concurrency models within the schema must be robust enough to handle high-volume, simultaneous requests. Misconfigurations in the schema roles or inadequate object grants can lead to session contention, effectively stalling the batch processes that run at the end of the day or beginning of the day. You will often find that the security model is tightly wrapped around these schemas, enforcing strict role-based access to limit who can query sensitive customer data. Audit trailing is integrated deeply into these structures, ensuring that every modification to a transactional record is logged according to institutional requirements. By respecting the predefined schema structure and avoiding the temptation to implement ad hoc modifications, you ensure the system remains within its supported state, which is vital for long-term stability and patch deployment compatibility. See you in the next lecture. Welcome to our exploration of the Oracle FLEXCUBE Data Dictionary, a fundamental aspect of your preparation for the 1z0-413 exam. In this lesson, we will dissect how to navigate the complex metadata structures that define the core banking environment. When we interact with an enterprise-grade banking platform like FLEXCUBE, we are essentially operating on top of a highly abstracted layer that sits above the physical database. The data dictionary serves as this architectural map, informing the application how to interpret table relationships, column constraints, and view definitions. Unlike a standard relational database implementation, FLEXCUBE relies on these metadata layers to generate screens, handle validations, and enforce business rules dynamically. To effectively navigate this, you must look beyond standard SQL queries and understand the underlying Oracle metadata views that store the system's structural DNA. Mastering these views allows you to troubleshoot issues ranging from UI field mapping errors to unexpected behavior in core banking modules. At the heart of our navigation strategy is the distinction between system-defined tables and the metadata definitions held within the dictionary. You will frequently encounter scenarios where a field appears in the user interface, yet its persistence behavior is controlled by a specific dictionary entry rather than a simple database trigger. When you audit the schema, focus your attention on the views that capture the mapping between the physical column and the logical business entity. These entries are often referenced by the application's extensibility layer, which allows for customization without modifying the core source code. By querying these dictionary tables, you gain visibility into how the system dynamically constructs the data layer during runtime, which is critical for performance tuning and diagnostic tasks. Understanding the dependency graph within the data dictionary is just as important as knowing the location of specific tables. The FLEXCUBE platform utilizes complex synonym management and grants to ensure that the application server can interact with the schema securely and efficiently. As you navigate the data dictionary, pay close attention to how circular dependencies or excessive synonym chains might introduce latency in your queries. When executing standard verification tasks, your ability to map a UI component back to its schema definition depends on navigating these abstraction layers accurately. This skill is particularly vital during the deployment of patches or version migrations, where dictionary discrepancies can lead to broken UI elements or blocked processing. In the context of the Universal Banking exam, you are expected to demonstrate how these dictionary elements facilitate modular integration. Whether you are working with CASA, trade finance, or loan modules, the dictionary acts as the bridge connecting static storage to the logic defined in PL SQL packages. If a module fails to reflect custom parameters, your first step should be validating whether those entries have been correctly registered in the metadata repository. This involves inspecting the control tables that track state and configuration without needing to dive into the raw source code of the packages themselves. By keeping your analysis focused on these metadata markers, you maintain a cleaner, more sustainable approach to system administration and troubleshooting. Finally, consider how your navigation tactics support security and audit compliance requirements. Each entry within the data dictionary is bound by access policies that dictate which service principals can read or modify the metadata. When you are reviewing schema security, ensure that any custom dictionary entry follows the principle of least privilege, preventing unauthorized changes to the business logic definitions. Auditors often focus on the integrity of these metadata tables because they dictate the flow of transactions across the entire banking ecosystem. By maintaining a thorough understanding of how the system navigates its own dictionary, you ensure that the architecture remains robust, auditable, and fully compliant with technical specifications. We'll catch you in the next session. Welcome back. Today, we will dive deep into the core PL SQL packages that serve as the functional engine within the Oracle FLEXCUBE Universal Banking ecosystem. In any complex enterprise banking application, the database layer is far more than a simple storage repository. It functions as a highly orchestrated execution environment. Within the FLEXCUBE architecture, core PL SQL packages are the primary vehicles for enforcing business logic, maintaining data integrity, and ensuring that transactional consistency remains inviolable. These packages are not merely collections of stored procedures, but represent the formal encapsulation of banking regulations, interest calculations, and ledger posting routines. When you interact with the screen in the front end, you are essentially initiating a cascade of calls that drill down into these PL SQL packages to perform complex validations. Understanding how to navigate these packages is critical because they form the operational backbone that differentiates a generic database schema from a specialized financial transaction system. If you attempt to manipulate data directly without acknowledging the roles of these packages, you risk corrupting the transactional state. When we analyze the internal organization of these packages, we observe a distinct modularity that aligns with the different banking modules such as CASA, loans, or trade finance. Each module consumes specific utility packages that handle common tasks like date manipulation, currency conversion, and error logging, ensuring that the code remains dry or don't repeat yourself in a way that minimizes maintenance overhead. The architecture relies heavily on packages that act as entry points for service calls, often referred to as service layer packages, which then dispatch requests to domain-specific packages. This hierarchical structure allows the system to achieve a level of stability where a change in a specific calculation rule, such as an amendment to withholding tax logic, can be isolated within one package without destabilizing the entire banking engine. As developers or administrators, your task is to identify which specific procedures are invoked during a standard transaction flow, which often involves tracing execution paths through the data dictionary. Error handling and state management within these PL SQL units are equally paramount, particularly when dealing with high concurrency environments like end-of-day batch processing. These packages use standardized error-raising routines that propagate exceptions back to the application server layer, ensuring that the user or the integration interface receives a meaningful status code rather than a generic database failure. You must be comfortable with the way these packages manage session-specific data through package variables, which effectively maintain a temporary state throughout the duration of a transaction block. Whenever you are troubleshooting a failed transaction, your first step is typically to correlate the interface-level error with the package execution stack. By analyzing the global variables and temporary tables used by these packages, you can pinpoint the exact moment of failure, whether it is a business rule violation or a database constraint conflict. Security is intrinsically woven into these PL SQL packages through the use of execution rights and restricted access paths. FLEXCUBE does not allow arbitrary execution of all package procedures by application users. Instead, it enforces a strict security model where only authorized schema roles can trigger sensitive financial operations. This means that when you deploy custom extensions, you must be surgical in how you assign grants, as over-provisioning access can lead to silent security vulnerabilities within the core. Furthermore, these packages regularly interact with audit logging procedures that record every single mutation of the database, creating an immutable trail of activity that auditors will scrutinize. Maintaining the integrity of these audit calls within your own custom extensions is essential for keeping the system compliant with regulatory standards. Understanding the interplay between these procedures and the underlying schema structure is what separates an amateur implementation from a hardened, production-ready environment. See you in the next lecture. Welcome back. We are now diving into the essential database configurations that underpin the security and accessibility of the FLEXCUBE environment, specifically focusing on how synonyms and grants function within the Oracle schema. In any complex Oracle-based application like FLEXCUBE, keeping the database schema maintainable and secure is a non-trivial task. Synonyms provide an abstraction layer that allows us to reference database objects without being tethered to a specific schema owner. When you query a table, you do not want your application code to rely on hard-coded schema prefixes, as this introduces tight coupling. Instead, by creating a synonym, we create an alias. If the underlying schema owner changes or if the object is moved, we only need to update the synonym definition rather than refactoring the entire codebase. From an architectural perspective, this is a form of indirection that simplifies maintenance, especially when managing multiple modules that share common database objects. Think of this as the equivalent of an interface in software development, where we depend on a label rather than the concrete implementation detail of a schema-qualified table name. While synonyms handle the naming abstraction, grants are the fundamental mechanism for controlling access. In the multi-user, multi-modular environment of FLEXCUBE, the concept of the principle of least privilege is paramount. We must grant the minimum necessary permissions to the application users, or the service accounts, that interact with these objects. If a particular module, such as CASA or trade finance, requires access to a set of core banking tables, we do not simply grant broad, system-wide privileges. We specifically grant the necessary select, insert, update, or delete rights only on the required synonyms. This ensures that even if one component of the banking application is compromised, the blast radius of that security breach is physically contained by the database access control list. It is a form of defensive coding applied at the persistence layer, ensuring that our application users operate within the constraints of their intended function. Consider the practical scenario of a PL SQL package attempting to execute a procedure located in a different schema. Without a public or private synonym in place, the developer would be forced to use the fully qualified schema package name may notation. This creates a brittle dependency that breaks the moment we deploy across different environments or change our schema naming conventions. By creating a synonym for the package, the code remains clean, readable, and environment agnostic. Simultaneously, we must ensure that the user executing the synonym has been explicitly granted the execute privilege on the underlying object. If the access grant is missing, the synonym is effectively useless, leading to cryptic runtime errors that can be difficult to diagnose in a high-volume transaction system. Proper management of these two concepts, synonyms for structural navigation and grants for security authorization, is the bedrock of a stable Oracle FLEXCUBE deployment. The interaction between these two elements is often where complexity arises during patching or version migration. When you deploy a new version of FLEXCUBE application, you are often replacing large portions of the PL SQL code, which may involve dropping and recreating synonyms. If you forget to reapply the grants to the new object owner, or if you misconfigure the synonym to point to an outdated object version, the application will exhibit inconsistent behavior. This requires a disciplined approach, likely integrated into your automated deployment scripts, to ensure that the state of your synonyms and permissions is always in sync with the expectations of the application layer. By maintaining a clean mapping between your synonyms and the granted privileges, you reduce the surface area for unexpected bugs and lock-in, leading to a much more resilient database architecture over the lifecycle of the system. I will see you in the next lecture. Welcome back. In this session, we will focus on diagnosing and resolving common database-related issues within the FLEXCUBE architecture to ensure system stability. When we approach database troubleshooting in a FLEXCUBE environment, we must first recognize that the database is not an isolated component, but the heart of the entire multi-tier stack. Most performance bottlenecks or functional failures stem from a misalignment between the application server's expectations and the actual state of the schema. You should start your diagnostic process by checking the core PL SQL packages, as these often contain the business logic that handles transactional integrity. If a transaction fails, the first step is always to inspect the alert logs and the trace files generated by the Oracle instance. By cross-referencing these logs with the timestamps of your application errors, you can often pinpoint exact deadlocks or resource contention issues. Remember that FLEXCUBE relies heavily on specific synonym and grant structures. If these become corrupted during a deployment or a user role modification, the application will simply fail to reach the necessary underlying tables. Always verify your database connectivity pool settings on the application server side before concluding that the issue resides purely within the SQL layer. A common pitfall is ignoring the state of the session management tools, which can reveal hung sessions preventing necessary batch processing updates. Systematic isolation is your best friend when faced with an opaque error code, as it forces you to categorize the problem into either resource exhaustion, authorization failure, or invalid logical execution. In many production scenarios, we encounter performance degradation that looks like a database issue but is actually a byproduct of inefficient query execution plans. Even when the database schema is correctly structured and data dictionaries are fully populated, a change in statistics can cause the optimizer to choose a suboptimal path for complex core banking queries. You must be prepared to use tools like SQL Trace and TK-Prof to analyze what the database engine is actually doing during a request. If you notice a high number of consistent gets for a simple read-only screen, it is a clear indicator that your index strategy requires reevaluation, or perhaps a missing index is forcing a full table scan. Often, the resolution involves auditing the custom PL SQL packages that perform validations, as these can inadvertently trigger extensive lookup operations within the data dictionary. Do not overlook the impact of locking contention during periods of high concurrency, such as daily clearing cycles. When multiple threads are competing for the same rows in an account master table, the database performance will plateau regardless of hardware capacity. Identifying these contention points requires a deep understanding of how the FLEXCUBE application manages session state and how it maps those user actions into atomic database transactions. Another critical aspect of troubleshooting involves the integrity of the data dictionary and the underlying metadata that drives the FLEXCUBE screen designs. Occasionally, the application may fail to render components correctly because the metadata stored in the database tables does not match the deployment artifacts. If your data source mapping is incorrect, the application will be unable to resolve the necessary foreign key relationships that support the CASA or loans modules. I suggest you systematically check the views and synonyms provided by the core installation scripts to ensure that the environment is consistent across all tiers. If you encounter an abort during a batch process, specifically look at the status of the job queues and the specific error logs stored in the schema history tables. Often, a simple recompilation of invalid objects can resolve what appears to be a major system failure, especially following a patch deployment or a version migration. Never jump to restarting the entire server architecture without first examining the individual package state, as this can lead to unnecessary downtime and loss of transactional data. By maintaining a disciplined approach to reading system logs and understanding the interdependencies of the database objects, you effectively minimize the risk of prolonged outages in your banking environment. See you in the next lecture. Welcome back, as we now turn our focus to the UI Extensibility Tools chapter of the FLEXCUBE Universal Banking Architecture. We will examine how to adapt the system interfaces to meet specific functional requirements while maintaining architectural integrity. In the context of Oracle FLEXCUBE, UI extensibility is not merely about changing the aesthetic appeal of a screen, but rather about extending the base metadata-driven architecture to include custom data elements and behavior. The system utilizes a robust infrastructure that separates the user interface from the underlying business logic, which is a common pattern in enterprise banking platforms. By leveraging these tools, Developers can augment existing screens without modifying the delivered source code, which is critical for future patch application and version upgrades. We focus on the concept of metadata, which defines how fields, buttons, and data sources interact within the browser-based client. When you need to introduce a custom field that collects bank-specific information, you do not rewrite a Java class. Instead, you define the extension at the metadata layer. This approach ensures that the application server can continue to process requests in a predictable manner, adhering to the core functional specifications established during the initial deployment. To effectively use these tools, one must understand how the interface generation engine consumes form definitions. These definitions are stored in the database as specific blobs or metadata records that describe the layout, the data sources, and the event triggers for every transaction window. When a user requests a screen, the FLEXCUBE architecture renders the page based on this configuration, allowing for dynamic updates without recompiling the entire application. We treat the user interface as a living structure that reflects the transactional needs of the financial institution. Customization occurs by creating parallel metadata records that inform the engine to inject custom UI components into the standard view. This structural approach prevents the fragmentation that would otherwise occur if we force developers to manipulate the underlying JSP or HTML templates directly. Maintaining this separation is a mandatory requirement for any professional working toward the 1z0-413 certification, as it demonstrates an understanding of the product's long-term sustainability. The Extensibility Framework operates by intercepting the standard processing flow during the UI rendering phase to merge delivered metadata with your custom additions. This is typically achieved through the browser-based development environment provided within the FLEXCUBE ecosystem, which allows for the mapping of custom fields to data sources. You should approach these configurations by first identifying the intended data source, ensuring it aligns with the existing schema structures or the necessary extensions within the database. Once the data source is defined, you map the fields to the UI components, ensuring that the necessary validation logic is attached to the appropriate event hooks. These hooks provide a controlled mechanism to execute custom JavaScript when a user interacts with a field or submits a form. Because this happens within a structured framework, the integrity of the data transmission between the client and the integration layer remains intact, preserving the transactional consistency required by core banking modules. A significant portion of your technical work involves ensuring that these customizations do not introduce latency or stability risks into the user session. When we discuss UI extensibility, we are fundamentally discussing the extension of the object model that the FLEXCUBE client understands. Poorly implemented UI extensions often result in performance degradation, typically caused by inefficient event handling or unnecessary database round trips triggered by field-level scripts. You must minimize the logic implemented at the client side, preferring to offload complex business rules to the application server or the database layer whenever possible. By keeping the UI layer as a thin visualization component, you ensure that the system remains responsive, even when performing complex operations or handling large transaction volumes. This architectural discipline is the hallmark of a system architect who understands the implications of enterprise-grade software design and is something frequently tested in the certification environment. As you prepare for the exam, remember that the tools provided by FLEXCUBE are exhaustive and require a deep understanding of their specific syntax and declaration methods. You are not manually coding screens from scratch, but configuring a highly sophisticated engine. Practice identifying when a requirement necessitates a UI extension versus when it requires a change in the backend messaging or API structure. The distinction is crucial, as the wrong approach can lead to significant maintenance overhead and difficulties during system migrations. Focus your effort on mastering the metadata structure and the life cycle of a screen request, as these are the core themes that will appear in your assessment. By maintaining this perspective, you will be well equipped to handle any questions involving the customization of existing screens or the implementation of new, compliant user interfaces within the 1z0-413 scope. See you in the next lecture. Welcome back, and let us turn our attention to the foundational concepts of user interface development within the FLEXCUBE architecture. In this session, we will examine the principles of screen design and how they interface with the broader application framework. When we approach screen design in FLEXCUBE, we are not simply drawing pixels on a canvas, but rather defining how the transactional logic is exposed to the end user through the browser-based interface. The architecture relies on an extensible development workbench, which serves as the primary tool for metadata-driven screen generation. By using this workbench, developers define the interface layout, including the positioning of input fields, buttons, and layout containers, without manually writing extensive HTML or JavaScript. It is crucial to understand that these screens are essentially dynamic representations of underlying data blocks. A screen is only as effective as the data model it represents. If you view the screen as a view model in a model view controller pattern, you begin to see why strict adherence to the metadata specifications is necessary. The metadata stored in the database governs how the browser renders the interface, ensuring that the same business logic is applied consistently regardless of the user's workstation. When you modify a screen, you are essentially modifying a set of XML-based definitions that the application server interprets at runtime. This abstraction layer is what allows FLEXCUBE to maintain a high degree of adaptability in complex banking environments where business rules change frequently. Therefore, your task is to maintain the purity of these data blocks to ensure that the screen remains both responsive and performant. To build a functional screen, one must establish a clear hierarchy of data sources and their corresponding UI elements. A typical screen layout in FLEXCUBE is built upon blocks, which act as wrappers for the data fields that interact with the database tables or views. As you design a screen, you must define the operational mode, such as whether the screen supports addition, modification, or query-only access for a specific functional module. Each field within a block requires a mapping to a specific data source column, alongside typecasting details such as text strings, numeric values, or date formats. You should always ensure that these definitions align precisely with the underlying schema to avoid runtime exceptions or data truncation during the save process. Furthermore, the positioning of these elements is controlled by properties that define the tab sequence and visual layout, which contributes to the overall user experience and workflow efficiency. If a user has to perform excessive manual entry due to poor field sequencing, the bank suffers from lower operational throughput. By properly organizing these elements within the workbench, you ensure that the generated UI is not only functional, but also intuitive for the bank teller or back office clerk. Remember that the design is a translation of business requirements into a structured, executable format that the system's runtime engine can reliably parse. Validation logic is inextricably linked to screen design, and you must consider it during the early stages of UI modeling. While it is tempting to push all validation to the front end for immediate user feedback, we must distinguish between client-side validation and server-side integrity checks. Client-side validations executed via the browser engine are intended for UX enhancements, such as checking for mandatory fields or pattern matching on formatting. However, these are strictly performance-oriented and cannot be relied upon as the final defensive line against invalid data entries. The true validation logic resides within the server-side PL SQL packages, which are invoked once the screen transmits the payload to the application server. When designing your screens, ensure that the fields are properly decorated with the necessary validation attributes to keep the user informed without compromising the integrity of the data tier. Failure to properly synchronize these two layers often results in confusing error messages, or, worse, data corruption in sensitive modules like CASA or trade finance. Always strive for a design that balances user responsiveness with the rigid security and integrity requirements of a core banking system. Transitioning into more advanced UI configurations requires a solid grasp of how menus and toolbars integrate with your newly designed screens. Menus in FLEXCUBE are not static structures, but are role-based artifacts that load dynamically based on the current user session context. As you design your screens, you must decide how they will be cataloged within the system's menu tree, ensuring that access rights align with the bank's internal security matrix. Proper menu definition is critical, as it serves as the entry point for all application functions. If a screen is well designed but hidden in an illogical menu structure, its utility is effectively zero. Furthermore, consider the use of standard buttons that perform common operations like save, delete, or unlock, as these are provided by the framework to maintain consistency across the system. By leveraging these built-in functionalities, you significantly reduce the amount of custom code required, which simplifies future upgrades and maintenance. As you iterate through your screen designs, Always test the menus to verify that the UI components render correctly upon selection. Consistent UI behavior across all modules is what defines a robust enterprise system, and this starts with meticulous layout and menu design. I look forward to discussing how these design principles translate into effective deployment in our next talk. Welcome back to our exploration of the FLEXCUBE architecture. In this session, we will focus on field validation setup within the UI customization layer. When we approach the task of field validation in FLEXCUBE, we are essentially defining the business rules that govern data integrity at the point of entry. The Oracle FLEXCUBE Development Workbench is the primary tool used for these customizations, allowing architects to attach validation logic to specific UI components without modifying the core source code directly. This is a critical distinction because the Extensibility Framework is designed to preserve your customizations during system upgrades and patch applications. By utilizing the event-based architecture, we ensure that validations trigger predictably during screen interactions like field blur or record commit events. Such predictability is essential when you consider that a single screen might involve complex dependencies between multiple fields across different data blocks. To implement a validation, you typically start by identifying the specific block and field within the screen layout that requires behavioral constraints. You have the choice between simple validations, which are often handled via static properties in the metadata, and complex validations that demand custom JavaScript functions. If you choose to write custom code, this must be integrated into the extensibility layer through the provided hooks, ensuring that the browser-side execution captures the data accurately before it is ever sent to the application server. It is important to note that client-side validation is primarily for improving user experience and reducing the number of unnecessary round trips to the server. Real security and data consistency, however, must always be enforced at the server level using the appropriate PL SQL stubs provided by the framework. Data source mapping plays an intrinsic role here, as the validation logic must have context regarding the source data block where the field resides. When you map a field to a data source, you are essentially defining the path through which the information flows, and any validation applied to that field must respect the underlying data type and constraints defined in the database schema. If, for example, a field is defined as mandatory in the database schema but is left empty in the UI, the validation logic must prevent the transaction from proceeding. Orchestrating these checks requires an understanding of how the FLEXCUBE framework manages state across the different tiers of the multi-tier architecture. You are essentially building a declarative layer that sits on top of the generic screen infrastructure to enforce specific banking business requirements. In terms of the actual implementation, the metadata for a screen defines how the system behaves when a user inputs data. During the configuration process in the development workbench, you can specify triggers that call validation functions. These functions are responsible for checking current field values against other related fields, or even against external data sources by invoking backend services. When testing these setups, it is common to use the browser developer tools to monitor the payload and the response from the server, as this highlights how the validation succeeds or fails before the data is committed. You should always aim for maximum code reusability by creating generic validation functions that can be attached to multiple similar fields, which keeps the code base maintainable and less prone to regression errors during system updates. The orchestration of these tasks demands a clear understanding of the interaction between the UI layer and the persistent storage layer. You need to verify that your field naming conventions match the data dictionary definitions exactly, otherwise, the mapping will fail during execution. Misaligned references are a frequent source of runtime errors that can be difficult to trace if you do not have a robust understanding of the underlying XML definitions that make up screen layouts. When deploying these validations, ensure that your environment configurations are synchronized across all nodes in a cluster to prevent inconsistent behavior for users moving between application server instances. System robustness relies on this level of attention to detail during the initial design phase of your UI customization strategy. Ultimately, successful field validation in FLEXCUBE provides a guardrail for operators, ensuring that only valid financial data enters the core transactional system. By effectively managing these validations, you reduce the workload on the back-end systems and minimize the potential for corrupted records that would otherwise require manual intervention. This approach aligns with the best practices of keeping the core flexible while making the front end highly responsive to the specific operational needs of the banking institution. As you master these techniques, you will find that the ability to intercept and validate user input is one of the most powerful tools in your customization toolkit. Always prioritize clarity in your custom code, as other developers will need to understand the intent behind your validation logic when they maintain these systems in the future. We'll see you in the next session. Hello, and welcome back to our deep dive into the Oracle FLEXCUBE interface layer. Today, we are focusing specifically on data source mapping, a fundamental concept for anyone configuring the user experience. In the FLEXCUBE architecture, the concept of a data source represents the bridge between the database schema and the UI layer. When you design a screen, the system needs to know exactly which underlying tables or views provide the data for the fields you have exposed to the end user. Data source mapping is essentially the configuration that ties a specific data source definition to the physical storage objects, such as base tables, audit logs, or join views. Without this mapping, the screen generator would have no context for how to perform CRUD operations or how to represent the relational integrity of the data within the browser. You should think of this as an abstraction layer that permits the UI developer to interact with business entities rather than raw database cursor handles. When you define a mapping, you are essentially establishing a contract that dictates how the application server should translate a field update from a form into a specific SQL execution. The mapping defines the scope of available attributes and ensures that mandatory fields are handled according to the defined business rules as they travel through the middleware. One of the most important aspects to understand when working with these mappings is the relationship between the primary data source and any child data sources that might be present on a screen. In a typical banking transaction, you often deal with a parent-child hierarchy, such as a loan contract header linked to multiple repayment schedules. To achieve this, the configuration requires that you specify join conditions and relationship types within the mapping metadata to ensure that the synchronization happens automatically. When a user requests to view or edit a record, the FLEXCUBE framework uses these mapping definitions to construct the necessary join queries dynamically. This prevents the need for hard-coding complex SQL inside the application logic, allowing for greater modularity and easier maintenance as business requirements evolve. If you mismap the foreign key references during this phase, you will inevitably encounter runtime errors when the system attempts to fetch related records that the database cannot reconcile. Consequently, precision here is not optional, as it dictates the integrity of the data displayed throughout the entire transactional lifecycle of the banking platform. Furthermore, you must consider the performance implications of how these mappings are structured within the application server environment. When you link a data source to a view, the underlying SQL execution plan becomes dependent on the complexity of that view. If the mapping points to a complex union or a nested join, the latency for rendering a simple screen will increase significantly because the database engine must work through the overhead each time the user refreshes or saves data. Advanced architects often use materialized views or optimized indexes to alleviate these bottlenecks, but the mapping configuration itself must remain aligned with these database-level optimizations. You also need to pay attention to how the system handles null values and default attributes during the mapping process. If a field in the UI is mapped to a column that does not allow nulls at the database level, and you have not defined a proper default value in the mapping, you will trigger a database constraint violation every time a record is persisted. These mappings also play a critical role in the auditing process, as they are often used to define which fields should trigger a history snapshot when they are modified. Finally, it is essential to manage the mapping metadata through the standard extensibility tools provided by FLEXCUBE, rather than attempting to manipulate the underlying C files directly. The framework relies on XML-based metadata descriptors that the server reads at runtime to build the UI models. By sticking to the provided tools, you ensure that your changes are captured correctly by the deployment scripts and can be migrated across different environments, such as from development to user acceptance testing. If you bypass these configuration layers, you risk creating a non-standard environment that will likely break during the next patch deployment or version migration. Always verify your mappings by performing thorough integration tests that simulate both successful transactional flows and expected failure scenarios. This ensures that the linkage between your UI screens and the database remains sound, secure, and performant throughout the operational life of the banking application. I look forward to discussing how these concepts interface with our next topic. Welcome to our technical deep dive into customizing menus within the FLEXCUBE architecture. In this session, we will examine the mechanisms required to modify application navigation and functional access points. When we approach the task of customizing menus in FLEXCUBE Universal Banking, we are essentially interacting with the metadata-driven architecture that separates the user interface from the underlying business logic. The system utilizes a hierarchical registry to determine which screens and functions are available to a specific user or role, and modifying these requires precise manipulation of the underlying configuration tables. Unlike simple web applications where menus might be hard-coded as static HTML, FLEXCUBE generates its navigational structure dynamically based on the state of the system registry. To change the menu structure, you must understand the relationship between function IDs and their corresponding positions within the menu tree. This is not merely about moving an option from one location to another, but about ensuring that the functional authorization remains intact for the end user. If you alter the structure without accounting for the role-based security layer, you risk creating orphan menu items that are visible, but essentially inaccessible. The primary tool for managing these modifications is the internal application browser and the associated function deployment tools that Oracle provides within the infrastructure. When you develop a custom menu, you are often working with a function definition record that contains metadata describing the entry point to a transaction or a report screen. This record must be registered correctly within the system's static data, specifically targeting the relevant modules that the menu item serves. You might encounter scenarios where a custom module requires its own dedicated folder or submenu to accommodate a specific workflow, such as a localized lending process or a specialized trade finance subinstrument. To accomplish this, you interact with the system's menu configuration tables, where you define the parent-child relationships that render the final visual tree. It is imperative to remember that these changes are global, meaning any modification to the menu structure will propagate across the environment once the cache has been refreshed. In terms of effective implementation, you must treat menu customization as a configuration deployment rather than a simple aesthetic update. This involves checking the specific menu access rights associated with each function ID, because simply adding a menu item does not automatically grant a user the right to launch the underlying function. The architecture checks the security profile defined for the user against the function ID attached to the menu item before rendering it in the browser. If a user lacks the specific execution privilege for an assigned function, that menu option will remain hidden or disabled, effectively mitigating security risks at the presentation tier. Experienced implementers always validate the menu structure against the organizational hierarchy before committing changes to the production database. You should also consider the impact of language localization on menu labels, as these are serviced through a centralized message repository that ties into the UI framework. Testing your menu customizations requires a methodical approach that mirrors the multi-tier deployment environment of your production system. After modifying the configuration, you must ensure that all relevant application server caches are cleared, as the menu tree is frequently cached to reduce the overhead of database round trips for every user session. Monitoring the logs during this phase is essential, as the system provides diagnostic indicators if a menu node refers to an invalid or missing function identifier. If you find that a menu option fails to render, check the database level constraints to ensure that the function ID is correctly mapped, and verify that the security role associations were not inadvertently dropped during the update. This level of technical oversight is what distinguishes a robust implementation from one that requires constant maintenance and debugging. By mastering these menu internals, you ensure that the end-user experience remains fluid and compliant with the bank's operational requirements. I look forward to discussing how these UI elements integrate with your broader scripting efforts in the next lecture. Welcome back. Today we examine the complexities of advanced UI scripting within the FLEXCUBE architecture. When we approach advanced UI scripting in FLEXCUBE, we are moving beyond the realm of simple drag-and-drop screen design into the territory of functional extensibility. The system provides the extensible markup language-based interface framework, but advanced logic often requires deep interaction with the internal JavaScript hooks that the platform exposes. You must understand that these scripts operate within the context of the client-side event model, which acts as a bridge between the user interaction and the server-side processing layer. When a field triggers an event, the script must be capable of executing asynchronous calls to perform real-time validations or data lookups without refreshing the entire document object model. This is where the mastery of the internal API libraries becomes critical, as injecting custom logic directly into the browser-bound FLEXCUBE engine requires precise adherence to the defined naming conventions and structural integrity of the function calls. Effective advanced scripting relies heavily on the underlying lifecycle of the screen, which developers often overlook when attempting to implement complex features. Each screen component follows a prescribed sequence of initialization, data binding, and destruction, and your custom scripts must hook into these lifecycle events at the appropriate moment to avoid null reference exceptions. If you intend to modify the data model or trigger an external service call, you need to ensure that your JavaScript functions maintain state coherence across these transitions. Consider the scenario where you need to perform a cross-field dependency check. Instead of relying on the standard declarative validation, an advanced script provides the granular control necessary to fetch values from secondary data sources. By manipulating the internal objects through the provided interface tools, you can dynamically show or hide fields and adjust mandatory settings based on the input of the current transaction, thus enhancing the usability of the core banking interface. Data source mapping is the cornerstone of any advanced script, and you should always prioritize leveraging the inherent bindings rather than force-feeding data via DOM manipulation. When a script interacts with the data source, it should treat the fields as mapped entities that adhere to the central schema rather than as transient visual elements. This ensures that when the final transaction is submitted, the business process layer receives data that fits the expected structure, preventing serialization errors that often plague poorly implemented extensions. You must be cognizant of the scope of your variables within the script, as global namespace pollution can lead to non-deterministic behavior in subsequent screen loads. Furthermore, performance should remain at the forefront of your design decisions, specifically by minimizing the number of synchronous calls that block the thread and cause perceived latency for the end user. Testing these UI extensions requires a methodical approach that mirrors the actual application deployment environment, as local execution environments often fail to replicate the security constraints of the enterprise application server. You should use the browser developer tools to verify that your script successfully registers its event handlers and that the data being passed matches the schema requirements of the backend PL SQL packages. If an advanced script interacts with a REST or SOAP gateway through the UI, you must be prepared to handle exceptions gracefully, providing meaningful feedback to the user when the backend service is unreachable. The objective here is to maintain a seamless user experience while ensuring that the custom scripting does not compromise the security or the stability of the universal banking application. By adhering to the architectural standards provided within the FLEXCUBE framework, you ensure that your work remains maintainable and compatible across subsequent version upgrades. I will see you in the next lecture. Welcome back to our exploration of the FLEXCUBE architecture. In this session, we will focus specifically on the role and configuration of internal messaging subsystems. When we consider the transactional backbone of Oracle FLEXCUBE, we must look beyond basic database operations and understand how the system facilitates data exchange across disparate modules and external interfaces. Messaging subsystems serve as the nervous system of this core banking platform, ensuring that requests, responses, and internal notifications are successfully routed according to predefined workflows. These subsystems are not merely passive conduits for information, but active participants in the transactional lifecycle, managing the translation and distribution of messages throughout the multi-tier environment. To effectively manage these subsystems, one must possess a granular understanding of how the internal message queue architecture interacts with the Oracle application server. When a transaction originates in a module such as CASA, the messaging subsystem determines the necessary routing path, verifies the data integrity against expected message formats, and ensures that the message is successfully enqueued for processing. Failures in this layer can lead to significant bottlenecks, often manifesting as locked records or stuck service requests within the infrastructure. In an enterprise environment, the messaging infrastructure often relies on the Oracle WebLogic message-driven beans to process asynchronous tasks, which allows the system to remain responsive even under high load. Configuring these components requires precise adjustments to the message-driven bean parameters, specifically paying attention to the transaction attributes and redelivery limits. If we misconfigure the persistence settings for a message queue, we risk losing transactional atomicity, which is unacceptable in a banking context where consistency is the primary constraint. Furthermore, the decoupling provided by these messaging layers allows for the distinct separation of duties between the front-end user interface and the back-end processing logic. We often see practitioners focus too heavily on the UI layers, yet the resilience of a system like FLEXCUBE is fundamentally determined by the stability of its underlying messaging pathways. You must ensure that the connection pools designated for messaging services are tuned to handle the peak traffic volumetric requirements of your specific deployment topology. Moving deeper into the technical mechanics, the ingestion of messages, whether they are internal system notifications or external communications, follows a strict pipeline that enforces schema validation before any processing occurs. This approach ensures that malformed data does not infiltrate the core accounting databases, thereby protecting the sanctity of the ledger. When we map these messages, we are essentially defining the interface contract between the FLEXCUBE core and the various service layers that provide specialized functionality, such as trade finance calculations or loan interest accruals. A deep familiarity with the messaging configuration screens within the FLEXCUBE workbench is essential for any administrator who needs to modify delivery channels or tweak routing protocols without resorting to manual database overrides. It is important to remember that these configurations must persist across environment shifts, meaning they should be version controlled in line with your deployment strategies. By mastering these configuration parameters, you shift from being a reactive troubleshooter to an architect who can influence the throughput and stability of the platform. Finally, let us consider the implications of security within the message flow itself, particularly regarding the propagation of transactional identity. As messages traverse the subsystem, the security context must be meticulously tracked to ensure that audit logs remain accurate and that performant role-based access control is respected at every node. If a message loses its authorization context during an asynchronous handoff, the application server might default to a guest execution model, which is a major compliance risk that would trigger audit failures. You should routinely verify that the message persistence stores are encrypted and that the communication channels themselves utilize appropriate transport layer security. This becomes even more critical when these internal messaging subsystems interface with external gateways, where the surface area for potential security vulnerabilities increases substantially. Keeping these subsystems locked down while maintaining high performance is the hallmark of a well-architected FLEXCUBE implementation. By prioritizing the structural integrity of your messaging subsystems, you build a foundation that supports long-term growth and complex modular integrations. We'll see you in our next session. Welcome back. Let us discuss how Oracle FLEXCUBE handles the transition and coexistence of Swift MT and MX messaging standards. In the landscape of modern core banking, the messaging subsystem acts as the central nervous system for interbank communication, and understanding how FLEXCUBE orchestrates this is essential. The older Swift MT, or message type, format is a character-based standard that has served as the backbone of financial transactions for decades. It utilizes a tagged format, where each line begins with a tag number indicating the nature of the data, such as field 20 for the transaction reference or field 32A for currency and amount. FLEXCUBE treats these MT messages as structured text files that the system parses through specialized message gateways. Because these are text-based, the validation logic resides largely in the parsing layer of the application, where incoming files are mapped to specific database tables for reconciliation. When you are preparing for the exam, remember that the reliability of these transactions depends on the accuracy of the configuration in the local branch parameters and the messaging queues. You must be comfortable with the way the system associates a specific transaction type with an MT format, as this mapping is what triggers the automated generation of outgoing messages during the life cycle of a payment. Transitioning to Swift MX, or Message XML, represents a significant leap forward in terms of data richness and machine readability. Unlike the rigid, space-constrained structure of MT, MX messages are built on the ISO 20022 standard using Extensible Markup Language, or XML. This format allows for a hierarchical structure that can accommodate a much larger volume of information without the limitations of character counts found in the legacy MT blocks. Within FLEXCUBE, the MX integration is handled by the messaging gateway, which supports complex XML payload mapping. When an MX message arrives, the system uses schema definitions to validate the structure of the incoming data before it ever reaches the application logic. This means that if an incoming payment does not align with the predefined XML schema definition, or XSD, the gateway will reject it at the perimeter. This is a critical distinction for the exam, as it highlights how the system performs structural validation before moving into business logic validation, which occurs later in the core banking accounting layer. The coexistence of these two standards creates a requirement for the system to perform complex translation and transformation tasks in real time. Many financial institutions still rely on MT for legacy connections while adopting MX for newer, high-value payment rails, meaning FLEXCUBE must act as a translator. This is often achieved through the internal mapping layers, where the system takes a dataset from an internal transaction object and generates either an MT text file or an MX XML document based on the recipient's capabilities. You need to understand that the gateway configuration is not just about routing. It is about defining the transformation logic that allows data to flow seamlessly regardless of the transport protocol. Security and audit trailing are also handled differently here. While MT messages provide a simple trail based on the file logs, MX messages allow for granular auditing of individual elements within the XML. During your certification exam, you will likely encounter questions that test your ability to distinguish between the processing requirements for these two message types, specifically regarding how they impact the overall performance of the messaging subsystem when dealing with high-volume batch transmissions. Finally, managing the messaging subsystem requires a deep awareness of how these formats interact with the database and the API layers. Both MT and MX payloads must eventually be persisted in a way that allows for efficient querying and reporting, which is why the schema design is so tightly coupled with the messaging layer. When you look at the messaging configuration, look for the synchronization between the outbound message queue, the gateway listener, and the business process definitions that govern the transaction approval workflow. Any improper mapping in the XML payload definitions can lead to processing failures that appear as cryptic errors in the application logs, often requiring you to inspect the raw message input against the active XSD to locate the mismatch. Mastery of this section is a clear indicator of a professional who understands the transactional backbone of Oracle FLEXCUBE. Catch you later. Welcome back. In this session, we will examine the mechanisms behind gateway integrations, a critical component for enabling external communication within the FLEXCUBE ecosystem. Gateway integrations serve as the primary conduit for external systems to interact with the core banking engine without requiring direct manipulation of the underlying database schema. When we discuss this architectural pattern, we are essentially looking at an abstraction layer that enables asynchronous and synchronous message processing between FLEXCUBE and third-party applications. The gateway is designed to sit between the core banking application and external consumers, such as a web portal, a mobile banking interface, or an enterprise service bus. By utilizing a standardized entry point, the system ensures that all incoming requests pass through robust validation protocols and authentication layers before they reach the core business logic. This separation of concerns is vital because it protects the integrity of the core banking state by enforcing strict input validation based on predefined XML schema definitions. Understanding the mapping of these payloads is non-negotiable if you aim to pass the exam, as it directly dictates how financial transactions are initiated and reconciled across different entities. The architecture of the gateway relies heavily on the definition of an adapter layer that translates incoming generic requests into actionable FLEXCUBE internal functions. When configuring these integrations, you are typically responsible for defining the service name, the operation name, and the associated data structures that define the payload contract. This contract is the absolute bedrock of interoperability. If your XML namespace or element hierarchy is misaligned, the system will reject the request before it even touches the internal processing queue. Furthermore, you must consider the deployment of these connectors within the application server environment, ensuring that the necessary listeners are registered to capture incoming traffic. I have often seen performance bottlenecks occur simply because the gateway listener was not appropriately scaled within the J2EE application server container, leading to thread exhaustion during high-volume periods. You should view the gateway not merely as a network pipe, but as a sophisticated state machine that manages transaction lifecycles from receipt to acknowledgement. From a functional perspective, the gateway facilitates interaction through two primary communication styles: the synchronous request-response pattern and the asynchronous event-driven pattern. In a synchronous flow, the external caller issues a request and waits for the system to process the transaction and return an immediate confirmation, which is common in balance inquiry scenarios. Conversely, the asynchronous model is typically employed for high-latency operations or batch-like inputs, where the system accepts the message, places it into a request queue, and returns an immediate correlation identifier. Mastering the distinction between these two modes is essential, especially when you're designing integrations that need to handle varying levels of transaction throughput. You must also become familiar with the way the system handles the correlation of these messages, which often involves specific tags within the XML header that link responses back to their originating request. For the exam, recognize that the configuration of these pathways often involves modifying the property files and the setup tables within the gateway's administration screens to map logical service names to physical database procedures. Data transformation is another area where many implementations encounter friction, particularly when dealing with legacy message formats like Swift, alongside modern XML-based structures. The gateway utilizes a mapping engine to parse these formats, and this engine must be configured to accommodate any custom fields or business logic extensions implemented in your specific regional deployment. When you implement a new integration, you essentially define the XSD schema that governs the request payload, which then acts as a template for the validation engine. If the incoming payload fails to adhere to the restrictions defined in this schema, the gateway effectively terminates the transaction at the perimeter, preventing invalid data from corrupting the core business tables. You should keep in mind that auditing requirements often mandate that every transaction passing through the gateway must be logged with a unique identifier, traceable back to the source IP and the user credentials provided in the request header. This level of granular visibility ensures that the integration layer remains compliant with financial security standards while preventing unauthorized access to sensitive account information through the API. I will see you in the next lecture. Welcome back to our exploration of the FLEXCUBE architecture. Today, we look into the specific mechanics of setting up the REST API layer within the banking environment. When we talk about RESTful services in the context of Oracle FLEXCUBE, we are essentially discussing the mechanism by which external systems interact with the core banking engine through standard HTTP methods. The architecture relies on the gateway infrastructure to act as a bridge between the outside world and the internal processing logic. Before any service can be consumed, the gateway needs to be explicitly configured to recognize and route the request to the correct application layer. This involves defining the service endpoints and ensuring that the underlying servlet containers can handle the inbound JSON or XML payloads effectively. You must keep in mind that unlike SOAP services which frequently rely on WSDL definitions, REST setup in FLEXCUBE is highly dependent on the correct mapping of resource URIs to the specific FLEXCUBE functional activity identifiers. If the mapping is incorrect, the gateway will fail to authorize the transition between the external call and the internal service execution. The configuration process begins at the gateway level, where you define the service provider and the corresponding interface types. You're essentially creating a bridge where the REST verb maps to specific operations within the FLEXCUBE application. It is vital to ensure that the security credentials passed in the HTTP headers are validated by the integration gateway before any processing occurs. I often see teams struggle because they overlook the necessity of the GWE gateway extension deployment on the application server. You need to verify that your resources are exposed via the proper URL patterns, which are controlled through the deployment descriptors of your integration modules. A common pitfall is misconfiguring the HTTP response types. So always ensure that your content type headers are set to application JSON or application/XML as per your integration requirements. Once the connectivity is established, we shift our focus to the payload structure and the validation engine. The REST layer in FLEXCUBE is not merely a pass-through. It performs validation against the data dictionaries we have configured in previous sections. When a request hits the endpoint, the gateway initiates a parsing routine where the JSON payload is transformed into an internal data format known as a data transfer object. If the input data fails to match the field-level validations defined in the screen or the data source, the service will return an error code, which you need to map to a user-friendly response. This validation occurs before the request ever reaches the PL SQL database packages, which is an intentional design choice to protect the integrity of your core banking schema. If you find latency issues here, you should investigate the complexity of the payload validation logic and verify if any large object serialization is slowing down the initial handshake phase. Managing the lifecycle of these API requests also requires a look at session management. Unlike synchronous stateful sessions, REST APIs are designed to be stateless, yet the core banking engine expects a valid user context to execute financial transactions. This means that for every REST call, the gateway must handle the authentication and session creation process efficiently to avoid overhead. You must balance the need for high-frequency transaction processing with the security protocols that demand frequent session validation. In a multi-tiered deployment, this usually means that the REST gateway resides in the DMZ, or the presentation tier, while the actual business logic remains locked in the application tier. Ensuring that these components communicate using secure, encrypted protocols is not just a configuration detail. It is a fundamental requirement for compliance and system safety. See you in the next lecture. Welcome back. In this session, we will examine the technical requirements and configuration pathways necessary to implement SOAP API services within the FLEXCUBE architecture. When we talk about SOAP API integration in the context of FLEXCUBE, we are essentially discussing the extension of the gateway infrastructure to allow external systems to invoke core banking services. Unlike RESTful services that might rely on JSON and lightweight headers, the SOAP implementation relies heavily on the Web Services Description Language, or WSDL, to define the contract between the requester and the provider. You must first ensure that the gateway infrastructure is properly initialized within the application server environment, as this acts as the primary traffic controller for all incoming requests. The configuration involves managing the interaction between the application's external interface and the internal PL SQL procedures that actually perform the banking transactions. If you have ever worked with enterprise service buses or complex middleware, this architectural pattern will feel quite familiar, as it prioritizes structure and strict typing over the flexibility often associated with modern web APIs. The setup process is not merely about enabling a toggle. It requires a deep understanding of how the FLEXCUBE integrated gateway consumes these service definitions and maps them to the underlying business functions. You are essentially creating a bridge that translates external XML-based requests into internal procedural calls that the database can execute. Consistency is the primary constraint here, as any deviation in the XML structure from the published WSDL will inevitably lead to processing errors that are difficult to debug in a live, high-throughput environment. The actual configuration typically begins at the deployment level, where the gateway service is enabled within the application server's JNDI namespace. You must verify that the connection pools designated for the gateway traffic are appropriately sized, as the overhead of parsing SOAP envelopes can introduce latency if not balanced correctly against the volume of expected concurrent requests. Within the FLEXCUBE console, you will interact with the gateway maintenance screens, where you define the service integration points and associate them with specific service providers. This is where you specify whether the integration should operate in an asynchronous mode through a message queue or synchronously, which provides an immediate response to the calling system. Each SOAP service needs to be mapped to a specific external interface in the system library, ensuring that the application server knows exactly which PL SQL package or Java component should be invoked upon receipt of a valid payload. As you navigate these screens, keep in mind that the system relies on the gateway maintenance and logger components to audit and track every single interaction. If you fail to configure these logging parameters, you will find yourself in a difficult position when troubleshooting failed transactions, as the visibility into the payload structure during the transport phase will be obscured. Pay particular attention to the security headers that are mandated by the SOAP protocol within FLEXCUBE, as these are distinct from the standard application-level authentication. The authentication process for SOAP requests often necessitates the inclusion of user credentials within the SOAP header itself, which the system must validate against the existing role-based access control policies. This means that a user or service account must not only exist within the database, but must also be mapped to the specific service provider configuration to be granted execution rights. If you neglect these mappings, the request will be rejected by the gateway layer long before it reaches the core banking validation logic, often resulting in obscure authentication errors in the server logs. Furthermore, consider the impact of SSL/TLS configurations on your SOAP endpoint, as encryption is a non-negotiable requirement for financial data transmission. All these moving parts must be verified during your integration testing phase to ensure that your setup is robust enough to handle production loads without unexpected timeouts or memory leaks. Complexity is, after all, best managed by isolating the transport layer configurations from the business logic. And that is exactly what the gateway architecture seeks to achieve here. See you in the next lecture. Welcome back. In this session, we will examine the technical mechanics of XML payload mapping within the Oracle FLEXCUBE Universal Banking environment. When we interact with the FLEXCUBE architecture through external integration points, we are essentially exchanging structural information that must conform to precise schemas. XML payload mapping serves as the bridge between the internal canonical data model and the external services that consume or provide banking transactional data. At its core, the system relies on an XML schema definition, or XSD, to ensure that incoming messages strictly adhere to the expected format. If a request does not validate against this schema, the transformation layer within the middleware will reject it before it ever touches the business logic. This gatekeeping mechanism is critical because improper data structures could lead to inconsistent states within core ledger tables. We must understand that Oracle FLEXCUBE treats the payload as an object that needs to be serialized or deserialized into memory-resident attributes. By defining these mappings explicitly, we enable the system to route data elements from an XML tags into specific database columns or PL SQL procedure parameters. The complexity of mapping arises when we consider the hierarchy of banking transactions, which are rarely flat. An incoming message might contain multiple nested nodes, such as a header, a payment body, and signature blocks that all require distinct handling. When configuring the interface, you are not merely defining a path, you are defining the translation logic that maps the external XML namespace to the FLEXCUBE internal field identifiers. If you're dealing with a standard message like a SwiftMT or MX conversion, the mapping utility manages the translation between the legacy tag-based system and the newer XML-based formats. We must concern ourselves with the precise namespace alignment, as any mismatch here results in parsing errors during the execution of the integration layer. It is this layer that acts as the executor, reading the configuration metadata you have defined to instantiate the correct business objects. This abstraction layer is what allows FLEXCUBE to support diverse integration partners without rewriting the core banking engine every time a new messaging standard emerges. Proper mapping also requires a deep understanding of how validation rules are mapped to the XML structure. When you design a payload mapping, you must define which fields are mandatory and which are optional, based on the business context. This is handled through the combination of XSD constraints and the internal validations within the FLEXCUBE Extensibility Framework. If a developer fails to link an XML node correctly to the designated data source handler, the system might fail to populate a necessary field, resulting in a null reference exception during the EOD processing. Furthermore, when dealing with complex data types, such as currency or account identifiers, the mapping configuration must include transformation functions that normalize data into a format that the banking system recognizes. These transformations are often managed via the interface configuration screens, where each node is mapped logically to the internal data dictionary. This ensures that even if external systems use varying data formats, the internal transaction logs remain pristine and auditable. We should also consider the performance implications of complex XML payloads. Large payloads require significant memory allocation for DOM parsing, which can lead to overhead if not managed through streaming parsers or optimized mapping configurations. As we configure the gateway for REST or SOAP interactions, we aim to minimize the depth of the tree and the number of nodes processed in a single transaction. This is why standardized integration templates exist, covering the most common banking operations like balance inquiries or fund transfers. By sticking to these validated mappings, we reduce the footprint of the XML transformation and increase the robustness of the system during high concurrency periods. For those developing custom integrations, it is imperative to use the provided integration tools to generate the documentation for these mappings. This practice ensures that the schema definitions remain static and that the integration bridge maintains its reliability even after system patches or updates. I will see you in the next lecture. Welcome back. In this session, we will examine the intricacies of user administration within the FLEXCUBE Universal Banking 12 environment. User administration in an enterprise banking platform is rarely a matter of simply creating a username and assigning a password. Rather, it is a foundational component of the system's security posture. Within FLEXCUBE, the framework manages identities through a centralized security layer that interfaces heavily with the back-end Oracle database. When an administrator provisions a user, the system does not merely store a record in a table, but defines a security context that dictates which branches, functions, and datasets that user can access during their authenticated session. This requires a solid grasp of how the application maps authenticated entities to authorization profiles stored within the core system tables. We must understand that user profiles are not isolated entities, but are deeply linked to the organizational hierarchy, which includes the branch structure and the specific business units where a user is permitted to operate. A common misconception is that administrative rights are binary, whereas in reality, these permissions are granularly controlled through a system of profiles and responsibilities that must be meticulously managed to maintain system integrity. Effective user management necessitates an understanding of the relationship between internal FLEXCUBE users and the external identity management systems that organizations often employ. While local authentication is possible, enterprise deployments typically leverage LDAP or similar directory services to centralize credentials, necessitating a clear mapping between these external identities and the internal roles defined within the application. The system architecture enforces a separation of duties, which is a compliance requirement that mandates we prevent any single user from executing transactions that require oversight by another role. Consequently, we define users who possess the authority to initiate a transaction and separate users who are empowered to authorize them, ensuring that the audit trail remains robust and verifiable. If you are configuring a system, you must ensure that the user creation process correctly assigns these roles to prevent unauthorized access to sensitive financial functions. This level of rigor is what distinguishes a well-configured banking core from a precarious setup prone to operational vulnerabilities or security breaches. Beyond the basic provisioning of credentials, user administration involves the careful configuration of access rights that determine what a user sees upon logging into the interface. FLEXCUBE utilizes a role-based access control mechanism, where permissions are cascaded from roles down to individual users, meaning that changes to a role propagate to every associated user automatically. This design choice is intended to simplify maintenance, yet it introduces the risk of inadvertent privilege escalation if a role is modified without considering the impact on all attached users. It is therefore critical to perform regular audits of the mapping between users and roles to ensure that access remains aligned with current job functions and internal security policies. Furthermore, one must consider the temporal nature of access, as administrators have the ability to restrict user connectivity to specific time windows, a capability that is essential for mitigating risk associated with offline hours or non-standard operational windows. By mastering these configurations, an administrator gains the ability to ensure that the human elements of the banking architecture remain secure and performant. See you in the next session. Welcome back. In this lecture, we will explore the fundamental principles of role-based access control within the FLEXCUBE Universal Banking 12 environment. When we talk about security in a core banking system, we are essentially talking about the integrity of the data and the processes that manipulate it. Role-based access control, or RBAC, is the primary mechanism through which we ensure that users only have the permissions necessary to perform their job functions. In FLEXCUBE, this is not merely a checkbox on a user profile. It is a sophisticated hierarchy that maps business duties to system capabilities. By decoupling the user from the permission set and placing a role in between, we achieve a level of granular control that is essential for compliance and internal security audits. Imagine a clerk processing a CASA transaction versus a manager approving a high-value loan. Their access requirements differ fundamentally, and the security architecture must reflect this duality without leading to administrative bloat or fragmented privilege management. The implementation of RBAC in Oracle FLEXCUBE relies on a structured approach where we define distinct roles containing specific access rights to screens, operations, and data sources. When a system administrator creates a role, they are essentially bundling functional privileges into a single logical entity. For instance, a user assigned the role of a trade finance operator would be granted access to the specific screens required for import or export documentation without necessarily having rights to modify core bank parameters. This is a design pattern that favors the principle of least privilege, ensuring that even if a user account is compromised, the blast radius of that breach is contained by the limitations inherent to their specific assigned role. Effective design here requires us to look at the business organizational chart and map it directly to the system roles, ensuring that no single identity assumes an administrative workload that it shouldn't possess. One of the most critical aspects of managing these roles involves the maintenance of the security data structures within the database schema. While the UI provides a way to assign these rights, the underlying records are stored in tables that control the visibility of functions and menus for the logged-in user. When a request hits the system, the application server validates the request not just against the user ID, but against the consolidated role memberships associated with that ID. This verification process involves checking the function IDs, which represent discrete operations within the banking modules, and cross-referencing them with the granted rights attached to the user's role. If a user tries to invoke an API or open a screen that falls outside their granted function map, the system will reject the request, typically throwing an authorization exception that needs to be logged for audit purposes. Complexity increases when you consider the interaction between multi-tier architectures in these access controls. In a standard deployment consisting of a web server, an application server, and a database layer, the role validation logic must be consistent across the board to prevent unauthorized access through alternative entry points like web services or batch interfaces. Developers often overlook the fact that REST or SOAP integrations also require a clear mapping of roles, as an API user is just another security principal within the system. If you misconfigure the gateway, you might inadvertently allow a service account to perform operations that are restricted for human users, creating a significant security gap. Therefore, it is imperative that your security model spans every entry point of the infrastructure, ensuring a unified policy that remains enforceable regardless of whether the request originated from a browser, a third-party application, or an automated batch process. Finally, let us consider the administrative overhead of maintaining these roles in an evolving environment where business requirements change rapidly. As banks expand their product offerings or reorganize their departments, the need for new roles or updated permissions becomes a constant factor in system maintenance. Rather than manually adjusting individual user profiles, which is error-prone and difficult to audit, the best practice is to refine the roles themselves so that all users inheriting those roles receive the update automatically. This approach essentially treats security updates as a form of configuration management, allowing you to maintain a clean and predictable security posture. Keeping your role definitions clean and well documented is not just a best practice for operational smoothness. It is a prerequisite for passing the stringent regulatory audits that are standard in the financial industry. See you in the next lecture. Hello there. Let us look into how we secure the system through robust password management. In this session, we will examine the specific mechanics of password policies within the FLEXCUBE framework. When we consider the security architecture of a core banking system, the enforcement of password policies is not merely a bureaucratic requirement, but a fundamental technical control. In FLEXCUBE, these policies are managed through the Central Security Administration module, which dictates how the application server and the underlying database interact with user identities. Unlike simple web applications that might rely on basic identity providers, FLEXCUBE requires a granular approach that balances security with the operational needs of high-frequency banking environments. We need to define parameters such as minimum password length, the complexity of character sets, and the prohibition of repeating past passwords. These settings are stored within the system parameter tables, which the application checks during every authentication attempt. When a user logs in, the authentication service validates these constraints before granting access to any branch or core banking module. If a password fails to meet the defined policy, the system must trigger an immediate rejection, logging the event for audit purposes. Consistency across the application tiers is vital here, as we must ensure that the password enforcement logic remains uniform, whether the user is accessing the system via the standard browser interface or through an API gateway integration. The lifecycle of a password in this environment is governed by policies that dictate age, expiration, and the grace periods allowed before an account is locked. From an architectural perspective, we have to configure these settings in the security profile associated with the user's role rather than the user ID itself. This is a critical design choice because it allows us to decouple security requirements from the specific identity, making the system easier to maintain when thousands of users are involved. We also have to consider the lockout mechanism, which is an essential defense against brute force attacks. When a user exceeds the maximum allowed attempts, the system flags the record in the database as locked, which then requires administrative intervention to reset. This workflow prevents unauthorized access, but introduces an operational overhead that the system administrator must manage through the relevant UI screens. We must also ensure that the audit trailing is active during these events, as every change to a security policy or an account status is a potential point of interest for compliance auditors. By centralizing these settings, we maintain a single source of truth for all security-related validations, which minimizes the risk of configuration drift across different modules or geographic branches. Another layer of this complexity involves how the application handles password history and synchronization. If your deployment uses an external identity manager or a centralized LDAP system, the password policy configuration inside FLEXCUBE might need to be synchronized to prevent conflicts between the two systems. We often see practitioners struggle because they fail to account for the precedence of policies when multiple security layers are enabled. You must verify that the password complexity requirements at the application level are at least as stringent as those at the identity provider level to avoid frustrating the end users. Furthermore, internal policies must prevent users from reusing their previous several passwords, which is a structural requirement that involves storing hashes in a historical record table. This historical record is checked at each change event. If you find your system performing poorly during heavy password reset windows, you should investigate the indexing on these security tables. Efficient lookup of historical password hashes is essential to keep the authentication process performant without compromising the security posture that we have defined. In practice, the implementation of these policies reflects our broader goal of system robustness and compliance. We are not just configuring text fields in a database. We are building a gatekeeper that protects the integrity of financial transactions and sensitive customer data. When you are designing your security strategy, think of the password policy as the first line of defense in the multi-tier architecture. It must be transparent to the legitimate user, but impenetrable to automated threats. As you grow comfortable with these configurations, you will see how they connect to the audit trails and session management tools we covered earlier. Everything ties into the goal of a secure, compliant banking environment that can withstand modern security scrutiny. Keeping these configurations clean and well documented will save you significant time during system audits or when addressing security troubleshooting alerts later in the lifecycle. I will see you in the next lecture. Welcome back to our technical walkthrough of the FLEXCUBE architecture. In this session, we will focus exclusively on the configuration and administration of audit trailing within the system. Audit trailing in Oracle FLEXCUBE is not merely a logging exercise, but a fundamental pillar of the system's security and compliance framework. To understand how to implement this, we must first look at the underlying audit trail architecture, which relies on the tracking of data modifications at the database level through internal triggers and application-level events. When a user performs an action, be it a financial transaction, a static data update, or a system configuration change, the system must capture who performed the action, what exactly was changed, and when the event occurred. This data is physically stored in specific audit tables, which are structured to serve as an immutable record of historical activity within the banking environment. Effectively setting this up requires us to define the specific functional modules and activities that necessitate auditing, as capturing every single system interaction would lead to a catastrophic degradation of database performance. We start the setup by identifying the target tables and the specific columns that fall under regulatory requirements for non-repudiation. Once the entities are identified, the audit configuration is managed through the Security Management System, or SMS, where administrators bind these audit rules to specific user profiles. It is vital to note that audit trail definitions are distinct from simple transaction logs because they require the preservation of the before and after state of the data, which is essential for forensic investigation during audits. We must ensure that the audit logging overhead is balanced against the need for traceability, which means that we typically configure high-frequency fields for audit only when risk profiles demand it. The actual implementation involves a layered approach where the application server communicates with the underlying database to trigger the storage of these audit records. When we configure the parameters, we are essentially telling the FLEXCUBE kernel which application events should fire an audit update. This is handled by a series of entries in the system's maintenance tables, which dictate whether an audit log entry is mandatory, optional, or irrelevant for a specific branch or transaction code. By correctly mapping these business activities to the audit subsystem, we create a reliable chain of custody for every data alteration. Developers and system architects often encounter the challenge of managing the growth of these logs, which can quickly consume valuable storage space in a high-volume banking environment. Consequently, our configuration must also account for a data archival strategy for these audit records, ensuring that we maintain active logs for real-time compliance checks while moving older history to cold storage. It is important to emphasize that once an audit configuration is active, the database triggers handle the population of these tables asynchronously to avoid introducing latency into the user's transactional flow. If the connection between the application's event handler and the audit table is broken, the entire transaction will fail to comply with security policy, which serves as a fail-safe mechanism. Therefore, maintaining the integrity of these linkages through constant validation is a critical part of your administrative responsibility. We also examine how role-based permissions interact with the audit trail, ensuring that while users can generate transactional logs, they do not possess the privileges to purge or truncate the audit tables themselves. By segregating these duties, we satisfy the core principles of internal financial control that regulators expect within an Oracle FLEXCUBE implementation. I look forward to our next session. Welcome back. Let us refine our focus on the infrastructure that keeps user interactions secure and consistent within the FLEXCUBE ecosystem. In this session, we will examine the mechanisms responsible for maintaining state and security during active client connections. In any enterprise-grade application like FLEXCUBE, the session management layer serves as the silent gatekeeper of user intent and data integrity. When an operator logs into the banking interface, the system must generate a unique identifier that correlates subsequent requests to this specific, authenticated context. This identifier functions much like a persistent memory for the application server, ensuring that a user's interaction with the CASA module